So far, you've learned how to build single agent systems. In this section, you will learn how to build multi-agent systems that use multiple agents instead of a single agent to accomplish complex tasks more effectively. More importantly, this section is about multi-agent patterns. Patterns are proven architectural blueprints for how agents can be organized, how they communicate, and how responsibility and control flow between the agents. Instead of building multi-agent system in an ad hoc way, patterns give you repeatable structures, showing you when to use hierarchies, when to use collaboration, and when to use collective reasoning. We will begin with an introduction to multi-agent systems, what they are, why they matter, and when to move beyond a single agent. Then you will learn the agent as a tool pattern, where agents are used as specialized tools inside another agent's reasoning loop. Next, we'll cover the supervisor and the hierarchical patterns, followed by the consensus pattern, where multiple agents independently reason and a final answer is synthesized from their outputs. I'll then introduce you to the LangGraph swarm package, which provides building block for the swarm pattern. By the end of this section, you will understand how to design and implement multi-agent systems using proven architectural patterns instead of ad hoc designs. In this lesson, we'll build the foundation for multi-agent systems. We'll start with the motivation, why complex problems often require more than a single agent. Then we'll look at a few real-world use cases where multi-agent systems naturally fit. Finally, we'll examine the advantages and challenges so you understand both the power and the trade-offs of this approach. By the end, you will have a clear sense of when and why to use multi-agentic systems. Imagine a patient with a rare disease visiting their primary care doctor. The doctor is skilled at common medical issues but may not know every rare condition. Now, to provide the best care, doctor refers the patient to a team of specialists. Each specialist contributes their expertise and together they create an effective recovery plan. This collaborative approach leads to a much better outcome than if the doctor had worked alone. Now, a multi-agent system works the same way. It's a group of AI agents, each specialized in a particular task, working together to solve a complex problem. Collaboration between agents allow the system to achieve results that a single agent working in isolation could not. The key idea of multi-agent systems is that a single agent may be insufficient for handling complex tasks. The main motivation for using a multi-agent system is to enhance performance and tackle complex open-ended problems that are difficult or impossible for a single agent to solve alone. Each agent in a multi-agent system specializes in a specific area with its design fully focused on that expertise. Its system prompt contains highly detailed domain-specific instructions and strict constraints on response format, ensuring it operates within its narrow field of expertise. Its capabilities are defined by a curated set of deep task-specific tools such as dedicated API for medical diagnosis or financial data, rather than general-purpose utilities like web search. Furthermore, its reasoning is guided by domain-specific frameworks and knowledge bases which enforce specialized rules and validation checks, leading to structured, reliable outputs optimized for precision and accuracy in its designated task. A multi-agent system consists of multiple such agents that collaborate to achieve a common goal. The core idea is to decompose a complex task or problem into smaller subtasks, which are then assigned to the most qualified specialized agents. Now, if we extend our medical analogy here, imagine a modern hospital. Here, doctors with different specializations, like a cardiologist, a radiologist, a surgeon, they all collaborate, each applying their unique expertise to achieve the common objective of treating a patient. As an example of a complex use case, think of a software product development. Building a software product is a complex task, so it is broken down into multiple subtasks, each requiring a different area of expertise. A software development team is made up of individuals with these specialized skills acting like agents in a multi-agent system. The product owner is responsible for the creation of the product requirement document. The architect is responsible for designing the system. The UX expert focuses on the user experience. Developer implements the features, and the platform engineer ensures the underlying infrastructure is reliable, scalable, and secure. These agents collaborate closely to build the final software product. Now, such a result would be extremely difficult, if not impossible, for a single agent to achieve alone, because no one agent can perform all these specialized tasks effectively. I'm sure you have already seen in news the success of multi-agent system for software development. As another example, consider a customer support escalation system. Handling customer support effectively is a complex task, so it's broken down into multiple subtasks based on problem type and complexity. The process typically begins with a frontline customer support agent. This agent handles the initial customer queries such as account questions, basic troubleshooting, or common issues. When the problem becomes more complex, the task is handed off to a specialist agent. This could be a technical expert agent for deep system issues, or a contract specialist, or a billing specialist for payment and account related problems. Keep in mind that there can be multiple additional agents or experts depending on the use case. Each of these specialist agents focuses on specific subtasks, applying their expertise only when it is most relevant. The frontline agent filters and routes the request, while specialist agent resolve the more complex aspects of the issue. This handoff mechanism allows the system to scale efficiently and deliver faster, higher quality support, something a single general purpose agent would struggle to achieve on its own. Next, I'll walk you through the core advantages of multi-agentic system. The first one is distributed problem solving that improves efficiency through parallelism and enables adaptability by allowing agents to respond to local changes. For example, in a delivery logistics system, one agent may optimize vehicle routes, another may track inventory levels, and another may monitor real-time traffic or weather conditions. By distributing the work, the system reduces bottlenecks, it improves efficiency, and adapts more easily to changing conditions. The second core advantage is scalability and flexibility. Multi-agent systems can grow and evolve dynamically. New agents can be added when demand increases, and they may be removed when demand drops. Agents can also be heterogeneous, each optimized for different objectives such as speed, accuracy, or cost. The third core advantage is robustness and fault tolerance. Because agents operate independently, there is no single point of failure. If one agent fails, others can continue operating and may even take over the responsibilities or compensate through redundancy. Together, these advantages make multi-agent systems a powerful architectural approach for real-world production-grade AI systems. But there are challenges. Let's go over some of the common challenges. The first one is complexity in design and coordination. Designing a multi-agent system is a significant challenge. You must carefully define the roles, responsibilities, and communication protocols between the agents. Poor design can lead to chaos. Next one is communication overheads. Agents need to communicate, which consumes time and computational resources. Too much chattiness between the agents can slow down the entire system. Third challenge is that debugging can be difficult. When something goes wrong, it can be hard to diagnose. Was it a single agent's error or a miscommunication between two agents? Tracing the root cause is more challenging than in a single agent system. Evaluating these multi-agent systems is challenging because agents may take different valid paths to reach the same goal, making it difficult to check if they followed a predefined correct process. Next one is higher computational costs. Running multiple sophisticated agents can be computationally expensive and costly than running a single agent. It is important for you to keep in mind these challenges when deciding between multi-agent system and single agentic system. Let's go over the key points from this lesson. Multi-agent systems decompose complex problems into smaller specialized subtasks that are then carried out by independent agents. Agents collaborate to enable distributed problem solving, improving efficiency and adaptability. Multi-agent systems are well suited for complex, dynamic, and real-world AI applications. Starting with the next lesson, we will dive deeper into multi-agent system architecture patterns and see multi-agent systems in action. Happy learning, and I'll see you in the next video. In this lesson, we will cover the foundational patterns that enable agents to work together. We'll focus on the state management patterns, how agents store and share data, and communication patterns, how agents interact. You will see practical use cases for each of the patterns that I'll discuss. Keep in mind that the patterns that I'm covering in this lesson are foundational building blocks that form the basis for multi-agent system architecture patterns covered in later lessons. In any multi-agent system, agents must share information to coordinate and carry out their assigned tasks. In other words, they need to manage and share state. Let's look at three common patterns for state management. The first one is the global or shared state pattern. This uses a centralized synchronized data store like a shared memory space, which is accessible to all agents. Every agent reads from and updates this same shared state. The second one is the blackboard pattern. This is a more structured form of shared memory in which agents post partial solutions and read results asynchronously from a central blackboard. The agents are often designed to interact only with specific relevant parts of the data, contributing to a collaborative problem-solving process. The third pattern is the agent-specific or local state pattern. Here, There is no central store. Each agent maintains its own private or local state. Knowledge is shared explicitly through messaging. Agents send and receive structured messages containing only the necessary information. This creates a more decoupled and scalable system as agents operate independently and communicate by passing data directly to one another. Without clear communication patterns, multi-agent systems descend into chaos. Effective patterns are what enables coherent, coordinated action. Next, I'll walk you through some of the foundational agent communication patterns. The first one is the sequential handoffs. Imagine an assembly line or a relay race. In this pattern, agents interact in a strict predetermined sequence. Agent 1 completes the task, then passes the result to Agent 2. Agent 2 completes the task and then passes to Agent 3, and so on. The flow is linear, orderly, and simple to orchestrate. It's ideal for workflows with clear dependent stages like a pipeline for document creation that goes from research to drafting to editing. This pattern can work with different state management approaches. It can use a global state or blackboard, where each agent reads from and writes to a central store, or it can use local state management where the output from one agent is passed directly as a message to become input for the next agent, and the last agent spits out the final result. The key takeaway is that in sequential pattern, workflow and data moves in one direction, step by step, through a fixed chain of agents. Let's take a look at a use case for creative writing. In this pipeline, there are three agents: research agent, writer agent, and styling agent. Research agent has access to a web search tool to carry out the research. Writer agent specializes in writing a research report, and the styling agent specializes in transforming the report into a standard format using the styling guide as knowledge. The final output for this pipeline comes from the styling agent's response. Now let's look at a pattern that unlocks major performance gains: the parallel processing pattern. Unlike the sequential chain, here multiple agents work simultaneously on independent or partitioned tasks. Think of it as a team of specialists tackling different parts of the problem at the same time, rather than waiting for their turn in a line. This pattern often pairs well with a blackboard or shared state. The key takeaway here is that the parallel pattern is all about concurrent execution, where dividing and conquering leads to faster, more efficient outcomes. As an example use case, imagine processing a batch of customer reviews. Instead of one agent analyzing all the reviews in sequence, you could deploy multiple agents, one analyzing the sentiment, another one extracting the keywords, and a third checking for spam, all working in parallel on the same set of data. Since the agents are working independently, it will lead to a significant gain in efficiency. Now we come to the most flexible and decentralized pattern, the network or the peer-to-peer pattern. In this model, agents act in parallel. They act as peers in a network. They communicate directly with each other through peer-to-peer messaging without a central coordinator dictating the flow. Each agent can decide who to talk to, what to share, and when, based on its own goals and the messages it receives. This pattern naturally employs agent-specific or local state and explicit messaging. Knowledge is distributed and shared directly between peers. The key takeaway for this pattern is that it enables decentralized emergent coordination. The emergent coordination means that the overall system's organized behavior is not centrally planned or dictated by a single controller. Instead, it arises from the simple local interactions and decisions of the individual agents following their own rules. A good example for this pattern is the stock analysis for micro trading. In this simplified illustration, we have an agent that specializes in technical analysis, an agent that is continuously monitoring the market sentiment, and an agent that behaves and acts like a trader. The agents interact with each other to share information and to ask questions. They have a common objective, and that is to maximize the profit. In this lesson, we have explored foundational patterns for state management like shared state, blackboard, and local state or agent-specific state. And we also explored the communication patterns, sequential, parallel, and network pattern. In the next set of lessons, we will move from these building block patterns to architectural patterns such as supervisor, hierarchical, and the swarm pattern. Happy learning, and I'll see you in the next video. In this hands-on exercise, you will learn to build a multi-agent research system for generating reports on a given stock ticker. This research agent will give a recommendation on whether to buy, hold, or sell the stock based on the current news articles, state of the industry, and stock trends. Details for this exercise are available in the section Multi-Agent Systems. We will be building this research agent using LangGraph. And this is how the graph looks like. There are 3 nodes that are getting invoked in parallel. The industry research node wraps the industry research subagent. The stock research node wraps the stock research agent, and the stock trend analyst node wraps the stock trend analyst agent. Let's take a quick look at the code for these 3 subagents before proceeding forward. I've already opened the project repository in Jupyter Lab. The code that we are looking for is under the multi-agent finance subfolder, and here are the 3 Python files for our subagent implementation. Let's open industry research agent. This agent uses heavily search to fetch industry news articles. This class here represents the state for this agent, and we have a utility function, create industry research agent, that returns the actual agent. The way this agent is implemented is we have the prompt which says you are an expert in understanding the stock trends in a given industry sector. Generate the report. Here we are defining the Tavily search tool which this agent uses. Keep in mind that in order to use the Tavily search tool, you need to provide access to the Tavily API key, which needs to be set in your environment file. We are using the LangGraph create react agent function to create the actual agent. The other 2 agents are implemented on the same lines. Stock research agent uses the Yahoo Finance news tool, and the stock trend analyst agent uses the Yahoo Finance tool. At this point, I suggest that you pause the video, take a quick look at these 3 sub-agent implementation, and then join me for a walkthrough of the code for the research agent. The research agent is implemented in a Jupyter notebook, and you can find the code and explanation in the course guide, but let me walk you through the code and show it to you in action in the Jupyter Lab notebook. The notebook is available under the subfolder multi-agent portfolio research agent. The first thing we are doing here is importing all the required libraries. The most important part here is that you need to adjust the path to the environment file. Each agent can be adjusted to use a different LLM. This is the list of LLMs that are available. You can add additional models if you're interested. This is where we are defining the schema. This is a definition for the enumeration, a recommendation on whether to buy, hold, or sell the stock. This is the state representation, which is a shared state for the multi-agent system that we are building. The sub-agents update their respective attributes. So the stock research agent updates the stock research attribute, industry research agent updates the industry research, and the stock trends agent updates the stock trend research. The rest of the attributes are managed by the portfolio research agent. I'm also referring to that as the aggregator. So here is how we will create the finance sub-agents. We'll first initialize the LLM for the agent. As I was mentioning, you can change this index to use a different LLM, calling the utility function to create the actual agent, and then wrapping the agent with a function. And as you can see here in this function, we are simply invoking the agent with a message. The return from here has the attribute that is getting updated with the content from the sub-agent. And that's how we are creating the other two agents as well. Here is the code for the aggregator agent or the portfolio research agent. You are a stock research expert. You have access to the stock research, industry research, and the stock trends research. And you have to create the research report and make a recommendation. That's what this prompt is saying. So this is where we are creating the React agent, which is the aggregator agent. Note that we are not providing any tool to it, but in future implementations, we may also provide some tools to this agent. This is where we are creating the aggregator node, formatting the prompt for the aggregator node, invoking the aggregator agent, getting a response, and sending back the values for the various attributes. The next cell has the code for creating the graph with the aggregator. This part is pretty straightforward. We're simply putting together the nodes such that the three sub-agents get invoked in parallel. Let me run the code up to this point. And here is the graph. Let me go ahead and test this agent with the ticker symbol for Apple. And here is the final response from the portfolio research agent that used the stock research, the industry research, and the stock trend analysis to create the final report. And the recommendation here is to hold the Apple stock, and the agent has a confidence level of 0.75. So go ahead, try out this code on your own, make adjustments to it to carry out your own experiments. Happy learning, and I'll see you in the next lesson. In this lesson, you will learn how to build multi-agent systems using some of the common and proven architectural patterns. We will start with the supervisor pattern, where a central agent coordinates tasks and delegates work to specialized agents. Then we will build on that foundation with the router pattern and the hierarchical pattern. Finally, we'll cover the agent as tool pattern, where agents are wrapped as callable tools. The supervisor pattern is a multi-agent architecture where a central supervisor agent is responsible for coordinating the system. Instead of solving the entire problem itself, the supervisor analyzes the user's request. It then breaks the task into subtasks and then delegate those subtasks to specialized agents. And finally, it manages the routing of information from one agent to the other and generation of the final response. Each worker agent or sub-agent focuses on a specific capability. Supervisor agent invokes the agents, Supervisor can carry out the invocation sequentially or even parallelly. Supervisor receives the responses from the sub-agents, and then it uses or synthesizes those responses to generate the final response. Here's an example use case for supervisor pattern. Let's say we want to build a Q&A system for answering questions on financial industry. Supervisor in this case has access to multiple sub-agents. Each of these sub-agents specializes in different aspects of financial industry. Supervisor agent analyzes the question from the user and can decide on which sub-agents to invoke. Responses from the various sub-agents are then synthesized by the supervisor agent for generating the final response, which is sent back to the user as an answer. Now that you understand how the supervisor pattern works, let's talk about when you would use the supervisor pattern. The first reason for using the supervisor pattern is for complex task orchestration. You would use a supervisor when a problem needs to be broken into structured phases like planning, research, execution, and validation. Now, instead of one agent trying to do everything, the supervisor decides which specialized agent to invoke and in what order. For example, in an AI research assistant, one agent gathers sources, another summarizes them, and a third validates the conclusions. The second reason for using the supervisor pattern is for intelligent request routing. When different queries demand different expertise, the supervisor acts as a classifier and dispatcher. It interprets the user's intent and then routes the request to the right specialist agent. A common example is a frontline customer service agent that routes billing questions to one agent, technical issues to another, and account actions to a third sub-agent. This pattern derived from the supervisor pattern is also known as the router pattern. Third reason is for workflow automation systems. When tasks must follow business rules, dependencies, or approval flows, a supervisor manages control transfer between agents. Think of an enterprise automation platform where one agent extracts data from documents, another performs compliance checks, and another one that generates formal reports, all coordinated by a supervisor. The fourth reason is for tool-heavy AI systems. When agents rely on different tools, APIs, or execution environments, a supervisor ensures correct sequencing, monitoring, and error handling. For instance, in a data pipeline, one agent queries databases, another runs analytics, and another one that generates dashboards, while the supervisor orchestrates the entire flow. Next pattern is the hierarchical pattern. The hierarchical pattern is essentially an extension of the supervisor pattern, where some of the sub-agents can themselves act as supervisors, creating a multi-level control structure. So here in this example, we have one sub-agent which actually is implementing the supervisor pattern. This kind of a pattern enables recursive decomposition of problems. It leads to localized decision making and better scalability for complex systems. Think of a software development team as an example. In the team, there is a director who directly works with multiple team members, like the project manager, architect. These two are the individual contributors, but the director may also work with the tech lead, who can act as a supervisor for a team of UX designers as well as developers. So this is a use case for a software system built out of AI agents. The next pattern builds directly on what you have already seen with supervisors. The agent as a tool pattern is a multi-agent design approach where one agent is exposed to another agent as a callable tool or a function. The core idea is that sub-agent is wrapped with clearly defined capability, a structured input and output contract, and a narrow specialized responsibility. The controlling agent treats the specialized agent exactly like tools. It can invoke them on demand the same way it would invoke a search API, a database query, or a calculator. The controlling agent, which can be a supervisor or a React agent, decides when to call the sub-agent, what to pass into it, and how to use the result, keeping the orchestration centralized, predictable, and aligned with the workflow you designed. You will see this pattern in action in the next hands-on exercise. Let's go over the key points from this lesson. In the supervisor agent pattern, there is a controller agent that coordinates with other agents to achieve an assigned goal. The hierarchical pattern involves a hierarchy of sub-agents in which some of the sub-agents may be implemented as supervisors. Supervisor agent can act as an intelligent router. Such a use case of supervisor agent is known as a router pattern. Sub-agents can be exposed to other agents as callable tools, and this is known as the agent as tool pattern. Happy learning, and I'll see you in the next video in which you will see the supervisor pattern in action. In this hands-on exercise, you will build a stock expert agent that will be able to answer questions related to stocks. This agent will be built as a multi-agent system. It will use the specialized finance sub-agents that I walked you through in the earlier exercise. These finance sub-agents will be wrapped as tools. So by the end of this exercise, you will have a clear idea on how to build agents with supervisor patterns and how to apply agents as tool pattern. Details for this exercise are available under the section Multi-Agent System. You can follow the instructions here to try out this exercise on your own, or you can follow along and try it out with me as I walk you through the code for the supervisor agent. The solution for this exercise is available under the project repository subfolder multi-agent. Next, I'll walk you through the code and show you the Q&A system in action. I've already opened the solution notebook in Jupyter Lab. The first thing we are doing is importing the required packages. In order to run the code, you will need to switch the path for the environment property file. These are the default models available for the various agents. You can add your own models if you're interested. Now this is where we are applying the agent as tool pattern, creating an instance of the LLM. Recall that each of the sub-agents have a utility function that create a React agent. So here we are creating the stock research agent, and then we are defining the tool function. Within the tool function, we have the description of the tool, which will be used by the supervisor React agent. We are wrapping the ticker symbol that we are receiving in the tool function as an argument, invoking the agent with a message that contains the ticker symbol, and then returning the result. The same pattern is applied for the industry agent and the stock trend analysis agent. This is where we are creating the supervisor. This is a supervisor prompt. You are a supervisor agent managing multiple finance sub-agents as tools. And then there are rest of the instructions that you can read through. The agent creation is straightforward. We are creating the LLM instance for the supervisor agent and then creating a React agent, passing the 3 sub-agents as tools. This is where we are testing. Let me just go ahead and run a query. I have $10,000 worth of Apple stock. Is this a good time to sell? Let me just go ahead and run all the cells. This is where we are iterating through the response to pull out the tools that are getting invoked by the agent. So here, as we can see, the supervisor made calls to 2 tools, stock trend analysis tool and the stock research tool. Let's try out a different user message. Let me just say, what is the recent stock price for Apple? Let's run this and see which tools the supervisor agent is going to use. This time, as expected, only the stock trend analyst tool was used. So the difference between this exercise and the earlier exercise is that in the earlier exercise, all of the 3 sub-agents were invoked in parallel, and then the aggregator agent used the results from all 3 agents to generate a report. In this exercise, the supervisor agent is making a decision on which tools to use to answer the question. Happy learning, and I'll see you in the next video. In this quiz, you'll check your knowledge of multi-agent system patterns. For each question, you'll get 10 seconds. If you need more time, please pause the video. Question number 1. What are the main advantages of multi-agent systems? The only wrong choice. The correct answers are robustness and fault tolerance, distributed problem solving, scalability, and flexibility. In fact, debugging becomes complex with multi-agent systems. Question number 2. Which of the following is not a common challenge in multi-agent systems? The correct answer is simplified evaluation matrix. All others are typical challenges in multi-agentic systems. Question number 3. What is the primary purpose of the supervisor pattern? The correct answer is to coordinate tasks and delegate work to specialized agents. Next question. Which of the following are state management patterns in multi-agent systems? The correct answers are global or shared state, blackboard pattern, and agentic specific or local state. Question number 5. What is the key characteristic of the hierarchical pattern in multi-agent systems? The correct answer is that some sub-agents can act as supervisor, creating a multi-level control structure. Next question. In the agent as tool pattern, how are specialized agents treated by the controlling agent? The correct answer is as callable tools or functions. Last question. Which communication patterns are commonly used in multi-agent systems? The correct answer is parallel processing, sequential processing or handoffs, and network or peer-to-peer communication. Happy learning, and I'll see you in the next video. In this lesson, you will learn how to design a multi-agent system using the consensus and the swarm pattern. The multi-agent consensus pattern is a design approach where multiple autonomous agents analyze the same problem independently and then converge on a final answer through an explicit agreement process. Each agent is typically given a distinct role, perspective, or a heuristic. For example, a risk focus agent, an optimization agent, and a domain expert agent, they work in parallel, producing separate outputs without influencing each other's reasoning. And then a consensus mechanism evaluates these outputs. This consensus process or mechanism can be as simple as majority voting. In this illustration, I'm showing a non-agentic consensus process that receives structured outputs from multiple voting agents. Because the responses follow a fixed schema, they can be reliably parsed by the code. The consensus algorithm can be implemented in multiple ways. For example, it can factor in the confidence scores or weightage along with the majority votes for making a final decision. Now, this illustration depicts a simple consensus mechanism driven by some kind of algorithm or code. In more advanced designs, a dedicated consensus agent can synthesize the voting agents or sub-agents output to produce a final response that integrates all perspectives and analytical viewpoints. In this pattern, the objective is not redundancy, it is robustness. Now, by forcing multiple independent reasoning paths, the system reduces hallucinations, it exposes edge cases, and it surfaces disagreements that a single agent would miss. Now, let's talk about when you would use this pattern. You see this pattern used in high-stakes scenarios in which correctness, bias reduction, and reliability matter more than raw speed. Examples of such scenarios are financial analysis and trading, wherein multiple agents assess the risk, valuation, market trends, etc. before executing the trades. Another one is medical diagnosis. Independent diagnostic agents analyze the patient data. Consensus improves accuracy and reduces misdiagnosis. Another one is legal or regulatory review, in which the agents analyze contracts, compliance, or regulations from different viewpoints. Next, I'll talk about the swarm pattern. The multi-agent swarm is an architectural pattern where multiple specialized agents collaborate as peers rather than being controlled by a central supervisor. When an agent receives a request, it can pass on the request to another agent. Now, you may ask, why would the agent pass on the control? It can happen if the agent realizes that it doesn't have the required domain knowledge, or it may not have access to the tools that it needs for generating a response. This passing of control from one agent to another is referred to as handoff. This handoff mechanism is the core idea behind the swarms. Key points to note here is that in the swarm pattern, agents are autonomous, specialized, and capable of routing work between each other without a central orchestrator or coordinator. In practice, a swarm works by giving each agent two capabilities: the domain tools, which are used by the agent to carry out the task, and the handoff tool, which is used by the agent for handing off the control to other agents in the swarm. Let me explain this with an example. Consider this implementation of a financial Q&A system built as a swarm. There are three agents in this swarm. The industry specialist agent may have access to web search tool that it uses to scan the web for news articles, industry outlook reports, and other type of information. The risk analyst agent has access to tools that it uses for fetching information on the time series data for market indicators, And then the compliance and regulations expert agent has a tool that provides it access to the SEC policies, rules, etc. The other capability that the agents have are the handoff tools. Each of these agents, as depicted in this illustration, have two handoff tools which allow them to pass the control to the other two agents within the swarm. When the handoff happens or the transfer of control happens, the full conversation state is preserved through a shared state. This means the receiving agent has access to the entire interaction history and the full user context. Let's check out how the swarm will work when the user will ask a question. In a swarm, one of the agents acts as an entry point in the system. Let's say the industry specialist is the assigned entry point for the system. The request or the question is routed to this entry point agent, which is the industry specialist. Let's say the question is around compliance and regulation, which SEC report needs to be filed every year. The industry agent analyzes the request and realizes that it doesn't have the domain specialization to answer this question. So it passes the control on to the compliance and regulation agent using the handoff tool. The compliance agent has access to the context and all interactions that have happened so far in the system. It uses its knowledge of the domain and the domain tools to generate the answer. Since the compliance and regulation agent is able to generate the final response, it is delivered as the final output from the swarm. Let's take a look at another example. In this example, the question is, what is the risk if annual SEC report is not filed by the public company? Now again, the industry specialist doesn't have the domain knowledge to answer this question, so it may pass over the control to compliance and regulations. The compliance and regulations agent will process this request, but it will not be able to answer the question completely as it does not understand the implications of not filing the report. So it may use the handoff tool to pass on the control to the risk analyst. Now the risk analyst will have access to the response from the compliance and regulations agent, and it also has access to domain knowledge and tools. So the risk analyst will be able to process the incoming request and generate the final response, which will be sent back to the caller. So here in this swarm, for this particular question, we see two handoffs. Swarm pattern is most effective when tasks and user interactions are dynamic, distributed, and domain specific. They shine in systems like customer support, where multiple specialist agents such as billing, booking, or claims need to interact directly with the users and hand off seamlessly. Swarms are also ideal for enterprise co-pilots, AI service desk, or sales assistants, where users move seamlessly between domains and require the right expertise at the right moment. Other use cases, financial planning that requires analysis and reasoning from multiple perspectives. Let's go over the key points from this lesson. Consensus mechanism can be algorithmic or it can be agent-based. In swarm pattern, there is no central coordinator or supervisor. Agents are able to communicate with each other, and handoff tool is used by the agents to pass the flow of control to other agents in the swarm. In the next lesson, you will see a multi-agent system that uses the consensus pattern. Happy learning, and I'll see you in the next video. In this hands-on exercise, you will build a multi-agent stock recommendation application that uses consensus pattern. Let me explain how this application will work. Details for this exercise are available in the course guide under the subfolder multi-agent systems. We will be using LangGraph, and we'll use the the finance agents that we have used in earlier exercises. Here is how the graph will look like. We will have three sub-agents: industry research, stock research, and stock trend analyst. The agents are wrapped with LangGraph nodes. Each of these agents will get the same input. They will generate a recommendation for a given stock, whether to sell the stock or buy the stock or hold the stock. The output from these three nodes or the three agents will then be sent to a consensus node. This node is wrapping the consensus agent that analyzes the output from these three nodes and generates a final output based on the analysis, the buy, sell, hold decisions, and the confidence score assigned to the recommendation by each of these agents. The final output is the buy, sell, or hold decision for a given stock, along with the reasons why the recommendation is being made, a confidence score, and an executive summary report. Now, you can follow the instructions on this page to build and run this application on your own, or you can follow along and check out the code and see it in action as part of this walkthrough. I've already opened the stock decision consensus notebook in Jupyter Lab. The first thing we are doing is setting up the environment and then setting up the state schema. Here, this is a decision enumeration. This is a stock recommendation schema, which is what we are expecting from the three agents. And this is the stock consensus state schema, in which we are holding the recommendation from the three sub-agents in the system. The final report is generated by the consensus agent, and these are the attributes that the consensus agent updates. There is a report, reasons, the decision, and a confidence score. So the difference between this confidence score and this confidence score is that this confidence score is assigned by each of the sub-agents, whereas this is the confidence score assigned by the consensus agent. Here are the three agents wrapped as LangGraph nodes. This is no different from the other code that you have seen in earlier exercises. The node is getting the consensus state as argument, creating a message, and then generating a response. This response follows the schema that I showed you earlier. So let's go ahead and run this. So the pattern for the three nodes is the same. And then comes the consensus agent. Now this is the important part. Here is the consensus prompt. You are a stock research expert. You will be given three independent research reports created by three experts. And here is the format of the reports from the three experts. This is the research input from the three experts. And here is how this consensus agent will carry out its task. Its task is to synthesize the three research inputs into a final recommendation for this stock. There are some instructions that we are providing that you can go through on your own. And here is how the output will look like. Go ahead, pause the video, go through this prompt to understand how this consensus agent will work. So here we are creating a React agent for the consensus and then wrapping the consensus agent with the consensus node and then creating a graph. Let me go ahead and run. Here is the graph and now we are ready to test. So let me go ahead and try out the stock with the ticker symbol GTM, run it. At this point, these three agents are running. They are carrying out the analysis using the tools that have been provided to them and generating a recommendation for the stock with ticker symbol GTM. Finally, the agent will carry out the analysis of the three recommendations and generate the final report that will be dumped out in the given format. And here is our final report. For GTM, the recommendation from the consensus is sell the stock. There's an executive report. And here are the reasons why the consensus agent is making this final recommendation. So at this point, I suggest that you go through the prompt that we have set up for the consensus agent to understand how the consensus is being carried out. Happy learning, and I'll see you in the next video. In this lesson, you'll learn about the LangGraph Swarm package that provides interfaces for creating handoff tools and swarms. In an earlier lesson, you learned how in a swarm, agents have access to two types of tools, the domain tools and the handoff tool. LangGraph core does not support the handoff tool. There is a separate LangGraph swarm library that provides an interface to create handoff tools. In the course guide under the Multi-Agent Systems folder, you will find an overview for the LangGraph swarm library. You may check out the actual implementation of the library in the GitHub. And also there is a video that I've embedded on this page for you to watch. I'll provide you an overview, but I highly recommend that you watch this video and also look through the assets available in the GitHub repo for the LangGraph Swarm library. Since it's a separate package, you need to install this package. There are two interfaces of interest in this package. First one is the create handoff tool, which allows you to create a handoff tool passed to the agent as a regular tool. In order to use this function, you need to provide an agent name. You need to provide a detailed description that tells what the agent does. And then there is also an optional name parameter. So here is an example, importing the create handoff tool from the LangGraph Swarm library, and then creating a handoff tool here using the create handoff function, providing the name of the agent, and then providing the description. Now, in order to create the swarm, you would use the create swarm function. You pass the agents as a list, and then you also pass the default active agent, which is the entry point into the swarm. This is the name of the agent. You can provide the state schema and the context schema. These two are optional. Here is an example use, create swarm, provide the list of agents, and then there is an entry point agent name that we are providing. This function returns a LangGraph. So in order to use this LangGraph, you need to compile it. Since the handoff tool behaves like any other tool, you can explicitly control which agents are allowed to receive the control. Let's look at a simple example. Imagine a system with three agents, A, B, and C. Agent A is given two handoff tools, one to agent B and one to agent C. So this means that agent A can pass control to both agent B and agent C. Agent B and C, however, are each given only one handoff tool to A. As a result, they can hand control back to A, but not to each other. To build swarms, you would use the LangGraph Swarm package. It offers two functions, one for creating the handoff tool and another function for creating the swarm. When you call create swarm, it returns the LangGraph graph that needs to be compiled. In the next lesson, you will see the use of these functions and a swarm system in action. Happy learning, and I'll see you in the next video. In this hands-on exercise, you will learn to build a stock Q&A system using the swarm pattern. We will use the LangGraph Swarm package to build this multi-agent Q&A system. Instructions for this exercise are available under the section Multi-Agent Systems in the course guide. This is how the graph for this multi-agent system will look like. As you can see, there is handoff happening between the industry research agent, the stock research agent, and the stock trend research agent. To run the code, you'll need to set up the environment property file that has the access to the model in use and the Tavily API key. Now, there are two ways to approach this exercise. You can follow the instructions in the course guide to create a notebook and run the code on your own, or you can follow along and learn to build a Swarm system with LangGraph package and see it in action. I've already opened the notebook in my Jupyter Lab environment. The first thing you need to do is install the LangGraph Swarm package. Here I'm just setting up the packages in use and the models that are available to us for use in this code. Make sure you switch this to your own environment property file. The default model in use is GPT-4.1 mini, but you can switch to any other model or add your own model. The first thing we are doing here is creating the handoff tools. This first handoff tool is to the stock research agent. The key point to note here is that you have to provide a name to each agent. So the first agent has a name, stock research agent. Then you describe what this tool does. Since there are 3 agents, we are creating 3 handoff tools. Each is given a unique name, creating the model instance to be used across the board in all the agents. Here is how I'm creating the stock research agent. This name must match with the name in the handoff tool. That's how the transfer of control happens. So in the stock research agent, we are creating the Yahoo Finance News tool as a domain tool. And in the creation process, we are passing this tool. And we are also passing the 2 handoff tools for passing the control to the other 2 agents. Similarly, we have the industry research agent with 1 domain tool and 2 handoff tools. And then we have the stock trend analyst agent with 1 domain tool and 2 transfer of control tools or handoff tools. To create the swarm, we are simply using the LangGraph create swarm function and passing it the 3 agents, also providing the default active agent, which is set to be the industry research agent. What that means is that when you will invoke the swarm, this is the agent that will receive the input, and it'll have the ability to hand over the control to the other 2 agents. Let me go ahead and run the code up to this point. And here is how our graph look like, and we are ready to test. Now I've given some example user messages that you can pass and test it out. Let's run the code with the question, what is the outlook for the semiconductor industry in 2026? Since the question is being sent to the industry research agent, it should be able to answer the question, and that's what is happening here. As you can see, the tool that got invoked is Tavily search. So the industry research agent is able to answer the question. Let me run another query here. This time I'm going to ask the question, do you expect to see the Apple stock price go up next week? The idea here is that the industry research agent cannot answer this question. As a result, it should carry out a transfer of control. And as you can see here, the industry research agent transferred the control to the stock trend research agent. And then the stock trend research agent executed the history tool to generate the answer. So go ahead and try out this code on your own with different queries to see the handoff of control. Happy learning, and I'll see you in the next video. In this quiz, you will test your knowledge of multi-agent patterns. For each question, you will get 10 seconds. If you need more time, please pause the video. Quiz number 1. What is the primary purpose of the multi-agent consensus pattern? The correct answer is to analyze problems independently and to converge on a final answer. Question number 2. Which of the following are characteristics of multi-agent swarm pattern. Select all that applies. The correct answers are agents are autonomous and specialized, and agents can route work between each other. This statement is incorrect. Handoff mechanisms are not used. In fact, they are used. And the second incorrect statement is there is a central orchestrator, which is not true about the swarm pattern. Next question. What is the primary difference between the consensus mechanism and the swarm pattern? The correct answer is that consensus uses a central decision-making process while swarm relies on peer-to-peer interactions. Next question. In the swarm pattern, what tool do agents use to pass control to other agents? The correct answer is handoff tool. Which of the following are suitable scenarios for using consensus pattern? The correct answers are medical diagnosis, financial analysis and trading, legal, or regulatory review. Question number 6. What is preserved when a handoff occurs in the swarm pattern? The correct answer is the full conversation state. Next question. What is the primary objective of the consensus pattern in multi-agent system? The correct answer is robustness. Last question. In a swarm-based financial Q&A system, which of the following should be considered domain tool for the agents? The correct answers are time series data tool for market indicators, web search tool for industry news, database of SEC policies and rules. These are the domain tools, and the handoff tool, obviously it's marked as handoff tool here for the agents. Happy learning, and I'll see you in the next lesson. Let me explain fine-tuning with an analogy of an accounting intern that you need to mentor. Think of yourself as an accounting expert in a company. Imagine the intern has already completed formal education in accounting. In other words, they have prior knowledge in the field. They understand the fundamental accounting principles, they're familiar with double entry bookkeeping, and they have some experience using accounting softwares. They also have basic grasp of tax laws and other general concepts that they learned during their education. To make this intern productive in your organization, you don't need to teach them basic accounting again. Instead, you need to extend their knowledge to include your company specific processes such as unique accounting practices, account categories, and the software systems used in your company. They'll also need to learn any industry specific tax regulations that apply to your business. With this additional training, the intern can become an effective and a valuable employee. As you can see, you didn't have to train the intern from scratch. They were already pre-trained in foundational accounting concepts. Fine-tuning an LLM is quite similar. The model already has general knowledge from pre-training, and you simply provide additional task-specific knowledge during fine-tuning. Now, let's consider how you would use this intern within your organization. If you want the intern to handle multiple general tasks, the additional training would need to cover a broader scope. This means you would teach them about your company's overall accounting processes, maybe provide a high level overview of different tasks without diving too deeply into any one area. For example, you would ensure the intern learns your company's accounting terminology across all accounting branches. They understand all applicable tax laws and they become familiar with the company's standard operating procedures, etc. In this case, the intern isn't being prepared for just one task, but is being equipped to handle a wide range of company specific accounting activities as needed. This is like domain adaptation of a pre trained model, where the model is fine tuned to work across various tasks within a specific domain, in this case, accounting. On the other hand, if the intern is being trained for specific tasks like handling accounts receivable or managing taxes, their training would have a narrow scope. Here, the focus is on making the intern proficient in a particular task or set of tasks. So they only need to learn the details of those new areas. This is similar to instruction fine-tuning of LLMs, where the model is fine-tuned to excel at specific tasks rather than general ones. To summarize, the key idea is that model fine-tuning is like training a new resource on company-specific tasks by extending their knowledge. Starting with next lesson, we'll start to dive deeper into the model fine-tuning. Happy learning, and I'll see you in the next video. In the earlier lessons, you learned about RAG and agents that can be used for building applications for accomplishing complex tasks. Sometimes, even with the advanced RAG and agent techniques, it is difficult to accomplish a domain-specific task with general-purpose pre-trained LLM. In this lesson, I'll go over the reasons why you may need to consider fine-tuning over other techniques for such domain-specific tasks. The first reason why you would need to consider fine-tuning over RAG is domain adaptation. Pre-trained models are typically trained on broad general-purpose knowledge corpus like Wikipedia, web crawl, etc. If your task involves working in a specialized domain like law or medicine, the pre-trained model might not perform well because it lacks the domain-specific knowledge. Consider a scenario in which you have to build a chatbot for lawyers. If you use general-purpose pre-trained LLM, the performance may not be optimal even with RAG. For example, the model will generate text that does not use appropriate legal terms or even use these terms incorrectly. A model fine-tuned with legal documents will have its knowledge updated. This, as you can imagine, will lead to model producing better results. For example, model will generate text that uses the right legal terms. The next reason is a common one, needing a model for a specific task. Your first approach might be to rely on prompting techniques, essentially seeing if the task can be accomplished using prompts and the pre-trained LLM's existing knowledge. If that doesn't quite work, you might turn to Retrieval-Augmented Generation or RAG. However, there may come a point where neither prompts nor RAG are delivering the results you need. That's when instruction fine-tuning becomes worth considering. Let's go over some signs that fine-tuning may be necessary. your prompt are becoming complex. For instance, the task may involve multiple steps and require a varied set of examples or scenarios for each step. It is extremely difficult or even impossible to explain the task patterns in the prompt. Even with advanced RAG techniques, the results are falling short. You may encounter edge cases where the model consistently misbehaves or performs poorly. Bottom line is that if you are noticing these signs, it's time to seriously consider fine-tuning. The next reason is to gain better control over the model's output. Imagine you need the model to generate marketing material. You would want the LLM to produce content that aligns with your company's traditional style. However, a general purpose pre-trained model won't have the specific tone, format, or style that you are looking for. By fine-tuning the model using past marketing materials, you can ensure that the output matches your brand's unique style, tone, format, and language, just like what your marketing team has consistently delivered. Recall that one of the LLM challenges is the dated knowledge. That is, the model doesn't have information on events that occurred after its pre-training. If your task relies on latest knowledge or data, you can pass that knowledge to the model in the context using tools and agents. However, if you are more interested in patterns in the data rather than the data itself, agents and other RAG techniques won't be effective. In such cases, fine-tuning can be done incrementally, which is referred to as continuous fine-tuning. The goal here is to keep the model's parametric knowledge up to date, reducing the need for complex application-level solutions to accomplish a task. This approach improves overall performance, enhances the model's efficiency in generating responses using its parametric knowledge. It reduces the number of input tokens required, and it simplifies the application's complexity. Another reason for fine-tuning is the need for enhancing the consistency in model's output. If you are seeing variability in model's responses for a given task, for example, the output is changing drastically even with minor prompt changes and you would like to keep it consistent, then fine-tuning can help you with addressing this need. Let's summarize the reasons to consider fine-tuning over other techniques such as prompting, RAG, and agents. You would consider fine-tuning if you would like the model to become better at domain-specific tasks. If you desire to get better performance for specific domain tasks, then fine-tuning is a good option. Fine-tuning leads to better control on the output generated by the model. You also learned about continuous fine-tuning, which keeps the model's knowledge up to date. And with this approach, you can reduce the application's complexity as the model will not require temporary knowledge or context to be passed with the new information. Fine-tuning also enhances the consistency and reliability for a task. So if you are seeing variability in responses for a task, consider fine-tuning. In the next lesson, I'll walk you through the fine-tuning process. Happy learning, and I'll see you in the next video. In this lesson, I'll provide you an overview of the steps involved in the fine-tuning of a model. The process will begin with the selection of a base model for fine-tuning. When selecting a base model, it's crucial to ensure that it aligns well with the specific task at hand. Suggestion is to define clear model selection criteria. One key criteria is the performance requirement. For example, if the task only requires around 80% accuracy, a large and complex model may not be necessary. Opting for a smaller, more efficient model can meet your needs while saving resources. Data security and privacy is another major consideration, particularly for enterprises. Many organizations prefer to avoid closed source model due to data privacy concerns, especially since these models are often accessed via third-party APIs. In such cases, self-hosted open source models can offer a more secure alternative. Cost is always a critical factor. The cost of using third-party models, especially the closed source models, can quickly add up. With self-hosted open source models, the costs depend on your infrastructure. So selecting a model that isn't excessively large can help reduce compute resource usage, resulting in lower operational costs. Consider the community and ecosystem support for the model as well. A strong, active community can make a huge difference, providing quicker answers to questions and troubleshooting issues. Also assess the model provider's commitment to the model family. You don't want to rely on a model that might be discontinued or lack support in the near future. Make sure the provider is committed to maintaining and supporting the model for a reasonable amount of time. Keep in mind that these are just some of the criteria or factors to consider. Feel free to add your own list of criteria or factors depending on your needs. At this stage, you should have selected a model family and a targeted model size. For example, if privacy is a concern, then select Llama family of model and self-host it. If performance is the biggest concern, you may want to select a closed source model such as GPT-4. Next step involves defining the evaluation strategy. Setting up the evaluation strategy before fine-tuning a model is like following a test-driven development approach for fine-tuning. In test-driven development approach, you write the test cases before developing the code, and similarly here, we are defining the evaluation criteria and preparing test cases for the model before the fine-tuning process begins. This ensures that we have a clear understanding of how to measure success and we can verify improvements effectively once the model has been fine-tuned. A common approach is to create a task-specific test or evaluation dataset with unseen data. This dataset should include edge cases to evaluate how the fine-tuned model handles novel patterns and unexpected inputs. By testing an edge case, you can assess the model's robustness in real-world scenarios. Evaluation is carried out with an automation that consumes the test dataset and generates a report. However, for some tasks, automating the evaluation may not be feasible. For example, tasks like fraud detection can easily be automated, as the output are typically binary or measurable. In contrast, tasks such as legal document summarization requires more nuanced evaluation, making it difficult to assess the quality of the output purely through automated means. For such scenarios, human feedback may be needed. Subject matter experts can evaluate the model's output by manually reviewing the response and scoring the model's responses. With humans involved in the feedback, scale becomes a challenge. So, to scale this process, you could use a larger LLM as an automatic evaluator, allowing it to judge the output instead of the humans. This can provide faster evaluations at scale. Such a use of LLM for evaluation is referred to as LLM as a judge. The next step is to prepare the data set. This step is crucial because the quality of the training data directly impacts the performance of the fine-tuned model. This step involves preprocessing the data set, such as removing the duplicates, formatting the data to fit the task requirement, and ensuring compatibility with the base model. It's important to ensure that the dataset is balanced. For example, for the fraud detection task, you should aim for an even split between positive and negative samples to prevent bias. You will also need to split the dataset into training, validation, and test sets to ensure proper model evaluation. In addition to quality, quantity matters. A small data set may cause the model to overfit, leading to poor generalization. When it is difficult to gather enough data, data augmentation techniques can be applied to generate synthetic data and boost the dataset size. Now we move on to the actual fine-tuning process. The specific steps will depend on the fine-tuning library or framework that you are using. For closed source models, you will typically fine-tune using the model provider's API or SDK, following their guidelines and tools. Next, you will execute the evaluation strategy to assess the performance of the fine-tuned model. If the results meet your expectation, the model is ready for inferencing. However, if the response quality is not satisfactory, you may need to adjust the hyperparameters and run the fine-tuning process again. Remember, this is an iterative process that may require multiple attempts to achieve the desired quality levels. If after adjusting the hyperparameters, the output quality is still not acceptable, you may need to revisit your fine-tuning dataset. You need to assess the dataset's quality, quantity, and coverage. I'll go into more details about dataset preparation and adjustments in a later lesson. In the worst case scenario, if adjusting the dataset still doesn't improve the output quality, you may need to consider using a different base model for the task. In this lesson, you learned about fine-tuning process. In the next hands-on exercise, you will create your first fine-tuned model. Happy learning, and I'll see you in the next video. In this lesson, I'll provide you an overview of tools needed for fine-tuning of open source and closed source models. You will also learn about the nuances of fine-tuning closed source models. Fine-tuning a large language model typically involves the use of machine learning libraries and frameworks. These libraries help manage tasks such as loading the training data, model architectures, optimization, and training. You can use common frameworks like PyTorch, TensorFlow, and JAX. Hugging Face Transformers library is one of the most popular and widely used tools for fine-tuning open source large language models due to its versatility, ease of use, and extensive support for various models and NLP tasks. The Transformers library abstracts the complexities. As a result, it makes fine-tuning straightforward. It is important to keep in mind that for fine-tuning, the machine learning frameworks and Hugging Face Transformer library requires access to the model weights and biases. Since the closed source model weights and biases are private, the standard machine learning frameworks and Hugging Face Transformers library cannot be used for fine tuning. Let's go over the comparison between open source and closed source fine tuning. I've already touched on public versus private weights and biases. For open source model fine tuning, there are a variety of machine learning frameworks and libraries. For closed source models, fine tuning is carried out using the provider's SDKs or API endpoints. In case of open source model, the fine-tuned model parameters are available to you, which means that you can self-host the fine-tuned model. In case of closed source models, the fine-tuned model weights and biases are not available to you. As a result, you need to depend on the model provider to serve the fine-tuned model for inferencing. Although I have mentioned provider SDK or API endpoint as the option for fine-tuning, there may be other options available depending on the provider. You would need to check the model provider's documentation for details. Each provider offers a slightly varying approach to fine-tuning. Let's explore some key aspects that vary between model providers. Datasets are the main ingredient for fine-tuning. Providers require data to be in specific format. JSON-L is the most common format supported by the providers. CSV is another commonly used format, but it is not as popular as JSON-L. Provider also require dataset to have specific attributes depending on the fine-tuning task. For example, the attribute names in JSON may be different for classification and summarization tasks. Then there are size restrictions on each example and on the total size of the dataset. Last but not the least, each provider recommends the minimum number of examples in fine-tuning dataset. These minimums depend on the task. As an example, let's take a look at the dataset requirements for the Cohere command model. This is the Cohere documentation website. Under the fine-tuning section, you will find the fine-tuning requirements for various tasks such as chat, classify, re-rank. Let's take a quick look at the dataset requirements for the classification task. As you can see, the Cohere command model supports fine-tuning for single label and multi-label. Here is a minimum recommended number of examples, which is 40 in this case. And there is also a suggestion on other characteristics of the dataset. For example, for each label, the dataset should have at least 5 examples. And it is suggested that there should be at least 2 unique labels. Here is an example of the dataset in JSON-L format for single label dataset. There are 2 attributes in each example, text and label. In the case of single label classification, the value for the label is a string. Here is the same dataset in CSV format with the headers, text and label. This is an example of multi-label dataset. The only difference is that the label attribute has a value of type array instead of a string. Next aspect is the hyperparameters for the fine-tuning job. Providers tend to simplify the fine-tuning process by simplifying the load on the user. They tend to expose only the essential model training hyperparameters to the users. Some providers expose additional proprietary hyperparameters. You will need to check the documentation to get details on the supported hyperparameters. As an example, Let me go over the hyperparameters supported by the Cohere command model. Let's check out the API reference. Within the API reference, we need to check out the fine-tuning. Within fine-tuning, we need to look for the API for training and deploying fine-tuned models. And here, the request needs to have the settings, which consist of the base model. And here is the attribute that we are looking for, the hyperparameters. These are the hyperparameters that are supported by the Cohere command model. Now, I won't go through the details of these hyperparameters. We will use some of these in the hands-on exercise. Suggest that you spend some time on quickly browsing through some of the APIs available for fine-tuning. Last aspect that I'll cover is the cost. Each provider has a different way of pricing the fine-tuning. In general, there are two price components for fine-tuning. First one is the direct one-time training cost, which depends on two factors: the size of the fine-tuning dataset and the number of times the model is exposed to the training dataset. It is controlled by the hyperparameter called epoch. Second component is the inferencing cost, which may be different than the base model inferencing cost. Let's check out the costing for Cohere models. I'm on the pricing page for the Cohere models. Here you will see that Command R model supports fine-tuning. The training cost depends on the amount of data that is processed for fine-tuning the model, and the current price as per their website is $3 per million tokens. This is the inferencing cost. As you can see, the inferencing cost for fine-tuned models is higher for the input as well as for the output. In this lesson, you learned about the tools needed for fine-tuning. Open source models can be fine-tuned using the common frameworks and machine learning libraries. Closed source models are fine-tuned using the proprietary capabilities offered by the model provider, such as SDKs and APIs. You need to check the provider documentation to learn the provider-specific dataset requirements, hyperparameter support, and the costs. In the next hands-on exercise, you will try out the fine-tuning for a multi-label classification task. Happy learning, and I'll see you in the next video. I'll begin this lesson by reviewing the objective of this exercise. Next, I'll explain how to fine-tune Cohere models. Finally, you'll get to fine-tune a model yourself and test it out. Let's start with the objective. The idea is to fine-tune a model for evaluating the toxicity of a user's comment in, let's say, a social forum like Reddit. Any comment that will have any of the toxicity labels will be tagged as such. The fine-tuning dataset is already provided to you in JSON line format. Now let's talk about the actual process of fine-tuning Cohere models. All hosted model providers offer REST endpoints for fine-tuning and model invocation. Cohere provides specific endpoints tailored to different tasks. In this example, I'm showing the fine-tuning endpoint and the classification task invocation endpoint. To submit a fine-tuning job, users can make a post request to the fine-tuning endpoint. Once the fine-tuning is complete, a new model ID is assigned to the fine-tuned version. Applications can then use this model ID for invocation of the fine-tuned model. In this example, I'm showing the Cohere SDK being used for initiating a fine-tuning job by invoking the fine-tuning endpoint. Cohere also offers a web UI for carrying out the fine-tuning. In this exercise, you will be using the web UI for fine-tuning. The instructions for this exercise are available in the course guide under the section fine-tuning. There are two parts in this exercise. In part number 1, you will fine-tune the model. In part number 2, you will invoke the fine-tuned model to check its accuracy. Let's go through part number 1. In step number 1, in part 1, we will check out the data set. Let me open this data set in a new tab. You will find that the data set has 5 columns. In the first column, there is comment text. This is the text which the model is going to look at and decide which all labels apply to it. There are 4 labels: toxic, threat, insult, and identity hate. Suggest that you go through this data set quickly to get a feel of its content. Next, you will use the Cohere web UI to initiate the fine-tuning job. You have all the instructions provided to you here with screenshots, so it's quite easy to follow. The training, validation, and test data sets are available in the project repository. The location is the subfolder fine-tuning data toxicity classifier. All of this data is in JSON-L format, and this is what we are going to upload to the Cohere web UI. Instructions are provided as to how to do that. So just follow the instructions and you will be able to create a job for fine-tuning. In part 2, you're provided a notebook. This notebook is available under the fine-tuning folder of the project repository. You can also open it in Colab. The first thing you need to do is get the model ID from the web UI for the trained model. Make sure that the model is in the ready state. Otherwise, you will see failure. So copy the model ID. You will paste it in the notebook and then run the evaluation task. So go ahead, try out this exercise on your own. And next, I'll show you fine-tuning in action. I'm on the Cohere dashboard. Click on fine-tuning. Click on classify, and we're ready to upload the training data set. And as you can see here, the validation set is optional. So I'm going to click on upload new. Select the training data set file for Cohere. Select the validation data file for Cohere. Add that. At this time, Cohere is validating the data in these files to make sure that all the requirements are met. Once the validation has completed, the review data button at the bottom will become enabled. Click on that. You can check out the stats for the training and the validation data, and then click on the button that says name fine-tune. Now we provide a name for the model. Let's call it multi-label toxicity classifier. We need to select the base model, select English, and click on Start Training. At this time, the fine-tuning job has been put in a queue. So keep in mind that the training doesn't begin right away, and it'll take some time for the training to complete. You can always go back to status and check how the training is progressing. Once the model training has completed, you are ready to move to part 2. Here, as you can see, this version of the model that I created a couple of days back is in the ready state. I can go ahead and use it. But a model that is under training cannot be used for invocation. Now, to use this model, I have to copy its ID, which I can do by clicking on this copy icon. And now I'll open up the notebook that we're going to use for testing this model. You'll see the usual stuff here. First cell has the code to set up the environment variables. Next step, you will see that there is a utility class called Cohere REST Client. This utility class uses the HTTP request package to make post calls to the Cohere endpoint for the classification task. Here is the invoke function that creates the payload. In the payload, it sets the authorization header. This authorization header has the Cohere API key. Here is how the payload looks like. This is the body of the post call. And here we are carrying out the unit testing. So let me go ahead and run this cell. Go ahead and carry out unit testing. This is where you need to set the model ID. Here I'm creating an instance of the utility class defined in the earlier cell. And now we are ready to invoke. Here I'm passing a single sentence as input, run it, and here is the output. As we have seen, invocation is successful. We're going to evaluate the model. To evaluate the model, I'm going to use the test data set. The way it'll work is I have the test data set available in a subfolder. Here we are reading the JSON file with the test data and creating two arrays, inputs and labels. And we are doing it just by reading the data from the test file. Let me go ahead and run it. Now we will invoke the model, and invocation will lead to the response that will have the predictions. After that, I am simply comparing the predicted versus the actual labels. And when I run this, we see that we are getting an accuracy of only 48%. Now, the reason we are getting this accuracy of 48% is because in the version 1 of the fine-tuned model, I used a data set which was a little skewed. But with the newer version, you should see a better result. Hope this gave you a good idea on how fine-tuning is carried out for closed source models. Happy learning, and I'll see you in the next lesson. I'll start this lesson by comparing the fine-tuning dataset requirements for domain adaptation fine-tuning and instruction fine-tuning. There are some differences in the datasets that you need to keep in mind. And then I'll describe a 6-step process for building datasets for instruction fine-tuning. When fine-tuning a model, a clear understanding of the task is paramount. Domain adaptation and instruction fine-tuning require different dataset considerations. Domain adaptation fine-tunes a model to specialize in a specific domain. For such fine-tuning, you would require general corpora as the dataset. Instruction fine-tuning teaches the model to better understand and follow explicit instructions provided in the prompts. This requires instruction response pairs or labeled data. Structure of the dataset for domain adaptation is the same as the datasets used for pre-training of the model. Whereas for instruction fine-tuning, you need to use the format that the base model requires. Domain adaptation doesn't require any specific instruction, whereas the instruction fine-tuning dataset also contains task-specific instructions. Example of data for domain adaptation are medical journals, books, articles, etc. Whereas example of data for instruction fine-tuning is a fraud detection task that require labeled dataset. Next, I'll walk you through the steps for preparing an instruction fine-tuning dataset. The first step is to identify sources of data. Here, the goal is to determine where you can find high-quality, relevant data that aligns closely with the task. Now, there are multiple sources that you may need to explore. The data from these sources may be combined to prepare the final data sets. For many applications, especially within enterprises, internal data sources such as transaction logs, user interactions, or proprietary documents are often the most relevant. For example, if you're training a customer service chatbot, then you would use the internal customer service transcripts for fine tuning. You've already seen that there are multiple high quality data sets available in the public domain. If relevant, you may use these public data sets. For example, SEC 10K annual filing dataset can be downloaded for any publicly traded company in US. It can be used for fine-tuning a model to predict the health of a company. Next one is the synthetic data. If real data is scarce or limited in quantity, you may generate synthetic data using different techniques. Especially with LLMs, it has become pretty straightforward to generate high quality synthetic data. The next step is to collect, clean, and label the data. The focus in this step is on building a high quality data set. Keep in mind that data quality is the main factor that decides the performance of the fine-tuned model. It is better to have a small set of high quality data rather than a large set of low quality data. At this stage, the data engineers are involved. They build data pipelines to connect with the data sources identified in the previous step. These pipelines must be designed to handle various data quality aspects such as handling of duplicate data, removal of the data that doesn't carry any relevance for the task, handling of the missing values or errors, and handling of the sensitive data. For example, sensitive data may need to be masked. And these are just some of the common tasks carried out via ETL processing. Once the data is cleaned, it needs to be labeled. Accurate and consistent labeling of the data is a must. For example, a model fine-tuned on mislabeled fraud detection dataset will provide responses that will be of suboptimal quality. Labeling can be part of the automation process, but for some tasks, it may not be possible to label the data with automation. For example, summarization of contractual document is a task that requires subjective review from humans. In that case, you will need to involve subject matter experts for labeling the data. Next step involves the balancing of the data set. Let me explain with an example what is a balanced data set. Consider a labeled fraud detection data set that has 80% example of not fraud and 20% examples of fraudulent transactions. When a model is fine-tuned on such a data set, there is a very high chance that it will be biased towards not fraud, meaning it will predict not fraud much more frequently than fraud, and that obviously will lead to poor performance. A balanced data set will have a 50-50 ratio of fraudulent and non-fraudulent transactions. Use of this balanced data set will lead to a better quality of predictions from the fine-tuned model. In short, balanced data sets improve the model's accuracy, robustness, and reliability, especially in real-world high-impact scenarios where fair performance across all classes is essential. Next step is data formatting, where we convert the model-neutral, cleaned and balanced data set into model-specific format. This is an important step as different models have specific structural requirements for the input data. The structural requirements vary even by the task for the same model family. For example, chat and classification tasks for the same model family might demand different dataset structures. Additionally, the data format must be compatible with the model's supported formats like CSV and JSON line. Next step is to split the data into training, validation, and test data sets. A typical split ratio is 70% of the data goes into the training data set, 15% goes into each validation and test splits. Fine-tuning process uses the training data set to adjust the weights and biases of the model, and it uses the validation data set for evaluating the model during the training process. Test data is not used during training. It is also referred to as unseen data. The test data set is used for offline evaluation of the model. Recall that in the last model fine-tuning exercise, you were provided with the data set that was already split. You uploaded the training and validation data set to the model provider's website for fine-tuning, and then you used the test data set for offline model evaluation. The last step is optional. In fine-tuning, augmentation involves creating synthetic data that mimics real data patterns. Augmentation is used when there is limited data available for a task. Augmentation is also used for balancing the data set. For example, an imbalanced data set for fraud detection may be biased for not fraud if it has more examples of non-fraudulent transactions. With augmentation, additional samples can be generated for the fraudulent transactions, thus balancing the dataset with 50-50 split of fraudulent and non-fraudulent transactions. And using this balanced dataset, you will achieve better results with the fine-tuned model. In this lesson, I described a 6-step process for building a dataset for fine-tuning. In step number 1, you would identify the sources of data for the fine-tuning dataset. These sources may be internal to your enterprise. If relevant, you may use public datasets, and you can also create datasets synthetically. Next step involves collection, cleanup, and labeling of datasets. The focus in this step is on quality of data rather than the quantity of data. This is the step in which data engineer creates a data pipeline. Automations may be used for labeling, but if automation is not possible for labeling, then humans are also engaged in the labeling process. In third step, you need to ensure that the dataset is balanced, as imbalanced dataset leads to poorly performing models. In step number 4, you need to format the data as per the base model format specifications and the task at hand. In the next step, you would split the data into training, validation, and test sets. And finally, step number 6 is augmentation. Augmentation can be used for expanding the dataset. It can also be used for balancing the dataset. Keep in mind, this step is optional. In the next hands-on exercise, you will work on building a dataset from scratch. Happy learning, and I'll see you in the next lesson. In this lesson, our focus is on preparing the dataset for fine-tuning the OpenAI 4o mini model. I'll start the lesson with a walkthrough of the objective and instructions on how you would prepare the dataset, and then I'll show you the fine-tuned model in action. In the last hands-on exercise, you used a multi-label toxicity classification dataset for fine-tuning a Cohere model. In this lesson, you will use the same data set, but keep in mind that every model has different structural requirements for the fine-tuning data set. So in this exercise, you would need to first understand the dataset requirements for OpenAI 4o model, and then you will need to put together some data processing code for preparing the dataset. Let's go over the instructions on how you would do it. The instructions are available in the course guide under the section Fine-Tuning. As a first step, you need to go over the requirements for the fine-tuning datasets for OpenAI 4o models. In step number 2, you will need to write some Python code to pre-process the data. You're already given Parquet files that contain the dataset that is already split. You'll find 3 Parquet files, one for each split. Once you have read the Parquet file, you need to convert the data in Parquet files to JSON-L format, which is what OpenAI requires the fine-tuning dataset to be. Since 4o Mini is a chat model, you need to provide the data in message format. Here, as you can see, there is a messages array that contain 3 messages. The first message is a system message where you instruct the model to behave in a certain way. So here we are asking the model to categorize the user's input in one or more categories. Second message is the text that needs to be labeled. Here the role is user and the content is set to the user's comment. The third message has a role assistant, which basically indicates the label, and the content has an array of labels that apply to the user's comment. So this is how each record in the dataset will look like. When you will execute the code, it will lead to the generation of 3 JSON-L files, one for each data split. In step number 4, you will use the dataset to fine-tune the OpenAI 4o mini model. Once fine-tuning is complete, you would open the fine-tuned model in Playground and test it out. The code for pre-processing is provided to you under the fine-tuning data subfolder. I suggest that you go ahead and try out this exercise on your own. Next, I'll demonstrate to you the 5th step, wherein I already have a fine-tuned model and I'm going to show you that model in action. I'm on the OpenAI dashboard. This is my fine-tuned model. And here you can see this button Playground. When you click on it, it opens a new screen with the base model and the fine-tuned version of the model. The first thing we need to do is provide the system instructions here. Let me go back to the course guide. The system instructions are already provided to you. Let me copy this and paste it here. The system instruction says you are responsible for content moderation for a public forum. For the given comment, you will categorize the user's input into one or more categories. Now, OpenAI Playground provides the same instruction to the fine-tuned version of the model. I'll pick up some samples from here. These 2 samples have been taken from test dataset. Let me copy this. This particular example has the actual labels toxic and insult. Let's see what our model will tell us. Here the base model predicted insult and the fine-tuned model predicted the insult as well, but it's in an array, which is what we would like the output to look like. Let's try one more. I'll copy the second sample. The second sample has 3 labels: toxic, insult, identity, hate. Let's go back, and here we have insult and identity, hate. And here, as you can see, we still got insult and identity, hate, but the output looks different with the base model. So I hope this gave you an idea on how you can prepare the data set for fine-tuning, and how you can test it. Happy learning, and I'll see you in the next lesson. For this project, consider this scenario in which you work for a bank and you are assigned the responsibility to build an API that will be invoked to detect fraudulent credit card transactions in real time. You proposed the use of a fine-tuned LLM for fraud prediction. Your management team told you that they will not invest in a new technology unless it can be proven that it'll work. So, to prove the feasibility, you decided to do a POC. Now, the challenge is that you do not have access to the real credit card transaction data for compliance reasons. So, to overcome this challenge, you have decided to synthetically create a balanced data set for fine-tuning an LLM for fraud detection. Your first task is to identify the data you will need to generate. To answer this, you consulted with a credit card fraud expert who shared a key set of indicators typically used in fraud detection for credit card transactions. The expert told you that while there are additional indicators, these are the critical ones that will effectively demonstrate the feasibility of the fraud detection API that you are building. With these insights, you now have a clear idea of the data needed for fraud detection. For more information on these indicators, we will refer to the course guide on the page titled Project Build Fraud Dataset. The details for these indicators are available in the section Fraud Detection Feature Set. Please go through this information on your own. Now, there are three parts in this project. In part 1, you will generate the synthetic data set in JSON format. In part 2, you will convert the JSON data into JSON line format and then split it into three parts. In part 3, you will balance the training data set. Fine-tuning, which is part 4, is optional, and I've provided a link to the instructions for fine-tuning. The solution to this project is available under the folder Fine-tuning in the project repository. You will find multiple JSON and JSON-L files which will be generated as part of the project, and you will also find a notebook that has the code for format conversion, splitting, and balancing. So go ahead, go through these instructions and try out this project on your own. Next, I'll show you the synthetic data generation in action. Let's start with part 1, in which the objective is to create a JSON file with some synthetic data. We will be using a prompt to instruct the ChatGPT to generate the data. Let me just copy this prompt, go to ChatGPT, paste it, and run it. And with this, we have ChatGPT generating some data for our review. Pay attention to what we have asked here. We have asked ChatGPT to generate only 5 examples. And this is so that we can review the data and make sure that it looks good. Here are all the indicators that we discussed earlier. The most important attribute is the transaction label, which is either set to not fraud or fraud. So that indicates whether the transaction represents a fraudulent transaction or a non-fraudulent transaction. You will also find there's a comment field. This data looks good. So what I'm going to do is generate the final data set by editing this prompt and change this to 80. Once you run this prompt, it will generate the 80 records. These 80 records then can be copied into a JSON file. Let's take a look at the JSON file here. In the project repository, under fine tuning, under data, synthetic credit card fraud, you will find the credit card fraud chatgpt.json, and you will see that there are 80 records in it. So at this point, we are done with part 1 of this project. Now we'll move to part 2. In part 2, we have to convert the data to JSON line format and then split it. And this part requires us to use some code. I've already provided you the code snippets that you can use for carrying out this task. Let's go ahead and open the notebook. The notebook is available to you under the fine-tuning subfolder in the project repository. Let's open it. Part 1 is done. We are at part 2. So let's take a quick look at what this code is doing. We are pre-processing the data to JSON line and splitting it. This is a pretty straightforward code. As you can see, I'm reading the credit card fraud chatgpt.json file and then creating 3 files under the subfolder synthetic credit card fraud. And this is the prefix for the 3 files that we will be creating. So we'll have a training file, a validation file, and a test file. Once you run this code, these 3 files will be created and you will also see the number of records in each of the file. Let me show you the data in these files. Under the synthetic credit card fraud subfolder, here is the training data set in JSON-L format. Similarly, you will find the test and the validation file. At this point, we are done with part 2 and we are ready to move to part 3, in which we need to balance the data set. Now, to balance the data set, first we need to check if we have an equal split of fraud and not fraud in the training data set. Now, we can count it manually, but a smarter way to do it is in code. So here you will find that we have the code to check if the data set is split evenly. So when we'll run this code, it'll go through the training data set, the training JSON-L file, and find out how many records have the fraud label and how many have not fraud label. We have 65% records for not fraud and 35% for fraud, which obviously indicates that the training data set is not balanced. Now, I also have some code that will tell us how many rows need to be added for which label to make it balanced. So when you run this code here, it tells you how many fraud records need to be created. So in step number 2, we will generate the suggested number of examples for the appropriate label. And this goes into a file name that indicates that this is additional data for augmentation. In the last step here, we are adding the content of this file into the training data set, and that creates a new file which is suffixed with the string -augmented. And this is the final file that will be used as training file for fine-tuning. Let me run this code. So additional examples were picked up and counted, and here is the final data set, which is balanced with 50% fraud labels and 50% not fraud labels. The idea is that now we can use this file to fine-tune a model which will not be biased. Before ending this lesson, let's go back to the files that were generated as part of the project. Here is the training data file that you will use for fine-tuning. This is the file that you will use for validation, and this is the file that will be used for testing the fine-tuned model. Happy learning, and I'll see you in the next lesson. The goal of this lesson is to introduce you to Alpaca, an instruction fine-tuned model that has gained significant attention for demonstrating the value of fine-tuning. In this lesson, you will learn how Alpaca was trained. A central aspect of the lesson will be the instruction dataset format, now commonly referred to as the Alpaca instruction format. Keep in mind that I'm providing a very high level overview of Alpaca. I highly recommend that you go through this blog to learn more about the Stanford Alpaca project and the Alpaca fine-tuned model. Instruct models, also known as instruct-tuned models, are fine-tuned language models designed specifically to understand and follow instructions effectively across a wide range of tasks. The Stanford Alpaca project aimed to explore fine-tuning of large language models to achieve improved instruction following capabilities. Specifically, the objective was to demonstrate that a relatively small and inexpensive fine-tuning process using instruction following data could significantly enhance a language model's ability to respond helpfully and appropriately to diverse prompts. Alpaca is an instruction following model that is a fine-tuned version of Llama 7B model. It was fine-tuned with 52,000 examples, also known as instruction instances. Alpaca was fine-tuned on 8 80GB NVIDIA A100 GPUs. It took roughly 3 hours to train it, and the cost of GPU usage was roughly $100. An interesting point to note is that the 52,000 instructions used for Alpaca fine-tuning were not created manually. They were created using a technique called self-instruct. Idea is that instead of manually creating the instructions for fine-tuning, a large language model can be utilized to generate the instructions. For more details on self-instruct, you can refer to this paper titled Self-Instruct Aligning Language Models with Self-Generated Instructions. Let's go over how the Alpaca instruction set was created using self-instruct method. Here is a high-level illustration that depicts the Alpaca fine-tuning process. To create the Alpaca dataset, the Alpaca team wrote 175 example instructions manually. These are referred to as the seed tasks. The seed task instructions were then used for generating 52,000 instructions using an LLM. Alpaca team used the OpenAI Text DaVinci model for generating these 52,000 instructions. The fine-tuning process was then run on the Llama 7B model as the base model, using the 52,000 instructions as the fine-tuning data. Although Alpaca team used the Llama 7B model, you may use any Hugging Face text generation model. Next, I'll go over the task coverage in the fine-tuning instructions. This illustration shows the distribution of top 20 task types included in the Alpaca fine-tuning dataset. Inner circle is a verb used in the description of the task. Outer circle are the 4 direct nouns related to the task. For example, some instructions sound like write a paragraph on the topic XYZ. Another example of instruction is make a list of ingredients needed for cooking pasta. Now comes the highlight for this lesson, the Alpaca instruction format. The Alpaca instruction format refers to the specific structure and style of instruction request-response pairs used in the fine-tuning datasets for Stanford Alpaca. There are 3 parts in each example. The first part is the instruction that describes the task the model should perform. Each of the 52,000 instructions is unique. Think of this as a specific task or command given to the model. Next one is the input. Input provides the context or input for the task. For example, when the instruction is summarize the following article, the input is the article itself. Since input is optional, it can be null. Around 40% of the examples in the Alpaca dataset have an input. Output is the desired response generated by the model for the given instruction and input. It is the answer or response to the instruction. Let's go over a couple of Alpaca instructions. In this example, the instruction is given an address and city, come up with the zip code. And the input is the address itself, output is the zip code. In this example, the instruction is write a letter from perspective of a cat. The input is null. And then you see the output, which is the response from the model. Now that you understand the Alpaca instruction format, let's check out the Alpaca dataset on Hugging Face. I'm on the Hugging Face portal. Here is where you will find the Alpaca dataset. These are all generated by the OpenAI Text DaVinci model. Let's just pick up the first row here. Here, as you can see, we have the instruction, the input, and the output. The text is actually a concatenation of the instruction, input, and output. In this first row, you will find the instruction is give 3 tips for staying healthy. The input is null, and there is an output that has 3 tips for staying healthy. Within the text, you will find that it begins with a generic instruction. Below is an instruction that describes the task. Write a response that appropriately completes the request. And then you will see there is a marker. Instruction prefixed with 3 hashes. And this is where the instruction goes. And then there is a response prefixed by 3 hashes. And then we have the response. This particular example does not have an input. Let's look for an example which has an input. So here, identify the odd one out is the instruction. The input is Twitter, Instagram, and Telegram. And then we have the output. Here, as you can see, in the text, we have the generic instruction. Below is an instruction that describes a task, etc. And then we have the instruction, the input, and the response. Alpaca team used the text as the input to the model for fine-tuning. I suggest that you pause the video and browse through the Alpaca dataset to get a feel of how it is organized and the various tasks that it covers. In general, any dataset that uses the Alpaca format is said to be an Alpaca dataset. Let's go over the key points from this lesson. Stanford Alpaca refers to a research project and a fine-tuned model. Self-instruct technique was used for generating the fine-tuning instructions for Alpaca. You learned about the Alpaca instruction format, which has 3 parts: instruction, input, and output. In the next lesson, we'll dive deeper into various fine-tuning dataset formats. Happy learning, and I'll see you in the next video. I'll begin this lesson with a discussion on instruction flattening. In the last lesson, you learned about Alpaca format. In this lesson, I'll introduce you to 2 additional formats: the Instruct GPT and Databricks format. You will also learn how to decide on the instruction dataset format. In the earlier section, we fine-tuned third-party models such as Cohere using the data in JSON-L format. Models may be fine-tuned using JSON-L strings, but it is common for the model developers to use flattened text instructions, which means that the structured and semi-structured data is reformatted for fine-tuning. Let me explain it with an example. You already know that the alpaca instruct dataset looks like this. This data shown in JSON format was not used as is for fine-tuning. It was formatted to this flattened text structure for fine-tuning. Pay attention to the JSON fields and the markers in the flattened text. The output field is replaced by the response marker. The model, as part of the fine-tuning process, learns the structural patterns in the fine-tuning data. And the implication is that for inferencing, you must use the data in the same format as was used during training, as it ensures consistency in how the model processes input data and generates the output. If the input format changes during inference, the model may not understand the data correctly, leading to degraded performance or even unpredictable results. Next, I'll introduce you to two commonly used instruction dataset formats. The OpenAI Instruct GPT format was used by OpenAI for training their Instruct GPT model. The instruction dataset consists of prompt response pairs. Databricks offer an analytics platform on the cloud. Databricks created a human annotated dataset called Dolly. The instruction data format used for Dolly is similar to Alpaca. There are three fields: instruction, context, and response. Do check out the Databricks Dolly dataset on Hugging Face. Now, so far I have discussed the message formats that are suitable for fine-tuning instruct models on common NLP tasks such as question answering, classification, summarization, etc. But these common data formats will not work for fine-tuning for chat models. For that, a common format that is used is the chat markup language or ChatML that was introduced by OpenAI. You will learn about the ChatML format in a later lesson. Now, let's talk about how you would decide the instruction format. If you are fine-tuning a base model, for example, BERT-based uncased, then you are in control of the instruction format. You may select one of the commonly used formats such as Alpaca, or you may create your own format. That is, you are in full control of the format of the instructions in the fine-tuning dataset. If you are fine-tuning an instruct model such as Gemma 2B IT, then you must use the instruction format used for fine-tuning the instruct model. Let's go over the key points from this lesson. For inferencing and fine-tuning of instruct models, the data must be in the same format as training data. In order to understand the format requirements for a model, you need to refer to the model documentation. Hugging Face datasets need to be formatted to meet the model's format requirements. Happy learning, and I'll see you in the next lesson. In this hands-on exercise, you will explore multiple datasets for instruction fine-tuning. Objective is to get an idea on how instruct datasets are formatted. Details of the exercise are available under the section Datasets in the course guide. I'm in the course guide. Here you will find the steps that you need to follow. The first step is to read through the blog on Alpaca project. I've provided the link here. I'll open it in a new tab. This is the blog that you need to go through. It'll give you a very good idea on how Alpaca was fine-tuned. You can also read about the self-instruct technique in the archive paper. This part is optional, but I will encourage you to read through the self-instruct technique. Next, you will check out the Hugging Face data sets for commonly used data formats. I've already provided the link here that will search the Hugging Face hub for data sets that follow the Alpaca format. Here, as you can see, this is the original Hugging Face data set used for fine-tuning the Alpaca model. In the third step, you will explore the Databricks Dolly dataset, and here is the link for it. Happy learning, and I'll see you in the next lesson. In this lesson, you will learn how the chat model fine-tuning datasets are prepared. I'll begin this lesson with an introduction to OpenAI Chat ML format, followed by a discussion on chat data format used for fine-tuning ChatGPT model. I'll end this lesson with an overview of how to prepare the chat dataset for fine-tuning. OpenAI Chat Markup Language, or Chat ML, provides a way to encode conversations as sequence of roles and content, enabling the creation of multi-turn conversation datasets for fine-tuning chat models. Essentially, what that means is that fine-tuning data follows the Chat ML format. The dataset is then flattened as per creators' fine-tuning preferences. This reformatted data is then fed to the base model for fine-tuning. In this illustration, I'm showing the fine-tuning of GPT model to create the ChatGPT model, which, as you know, is great for building multi-turn chat applications. In the Chat ML, a message consists of a role and content. The role can be one of the fixed personas. It can be system, assistant, or user. A sample in the Chat ML dataset consists of multiple such messages. Think of this as the message history for a multi-turn chat session. Here is how the Chat ML formatted instruction looks like in JSON format. It's a list of 3 messages. The first message is from the user, the second is from the assistant, and the third one is from the user. Recall that for fine-tuning, the messages need to be flattened as per the model developer's preference. It is a common practice to use special tokens for reformatting the Chat ML data for fine-tuning. Keep in mind that each model uses its own format and special tokens for formatting the Chat ML data to a format that is then used for fine-tuning and inferencing. A model developer may decide to use different role names than those used in Chat ML format. For example, system role is not supported by Gemma 2B instruct model. Next, I'll walk you through the chat data format used for training the ChatGPT model. Each message in a conversation sample is enclosed by special tokens. Here is a system message. This is the special token that indicates the start of the message. This token is followed by a role and a new line character. Then there is the message content. This is the special token that indicates the end of the message. Each of the messages follow the same pattern. Here is the second message, which is from the user. The final message is typically a response marker without the content or the special end token. This last message initiates the model to generate the response as an assistant. Typically, a formatting function or chat template is applied to the dataset to convert the conversation samples to model-specific chat messages. So here is how the overall setup may look like. Formatting logic takes as input the conversation in chat ML format. It applies the chat template and spits out the conversation data that is then fed to the GPT model for fine-tuning. Now let's talk about how you would prepare a chat data set for fine-tuning a base model. For base model, the chat template is not predefined, so you'll have to define your own chat template. You may use the pre-existing special tokens in the base model, or you may have to set up new special tokens that will be used in the chat samples. If you're using a fine-tuned chat model for further fine-tuning, then that chat model already has the predefined chat template that you must follow for further fine-tuning. Let's summarize the key points from this lesson. For inferencing and fine-tuning chat models, the chat data must be in the same format as the training or the fine-tuning data. ChatML is a commonly used template, but keep in mind that not all models support ChatML format. In the next hands-on lesson, you will learn how to format the chat fine-tuning datasets using the Hugging Face tokenizer utility function. Happy learning, and I'll see you in the next video. In this hands-on exercise, the objective is to learn how to prepare chat datasets for chat model fine-tuning. You will learn about the Hugging Face tokenizer chat templates. Then you will explore the chat ML datasets on Hugging Face. Finally, you will use the provided notebook to learn the chat templates supported by various models. I covered the Hugging Face tokenizer in the section on advanced Hugging Face models. The Hugging Face pre-trained tokenizer class is the base class for model-specific tokenizer classes. In this illustration, I'm showing the Llama tokenizer for the Llama family of models. If the model supports chat, then the model provider sets the model-specific chat template in its tokenizer. The pre-trained tokenizer class exposes the apply chat function that takes as input the conversation in chat ML format, and it returns the chat data in model specific format. Keep in mind that by default, a non-chat model does not have a chat template. For example, the Llama 3.3 70B instruct model supports chats. As a result, the tokenizer for this model has the template set up, whereas the Google BERT uncased does not support chat. As a result, it doesn't have a built-in chat template. You can check out the chat template for the model in the configuration file for the tokenizer. Let me show you how to do that. I'm on the Hugging Face portal looking at Llama 3.3 70B instruct model. Under the files, you will find the tokenizer config.json file. Within this file, search for chat template, and here is the chat template for the Llama family of models. This chat template is created using Python Jinja. I won't go through the details of Jinja templates. Please do your own research. Next, I'll walk you through the exercise. Exercise details are available under the section Datasets. Exercise number 4, prepare chat datasets. There are two parts in this exercise. In part 1, you will explore the datasets on Hugging Face that are in chat ML format. In part 2, you will use the tokenizer class to process the chat ML inputs. I've already provided the link for part 1. You can use this link for exploring the various chat ML datasets. In part 2, you are provided a notebook. This notebook has all the code that you need for exploring the chat templates. Let me walk you through this notebook. In order to understand the code in this notebook, you must have the basic knowledge of Hugging Face, transformers, tokenizer, and dataset classes. In the first cell here, we are setting up the environment variable HF token, as we will be using some gated models for testing. This array here contains the name of the Hugging Face models that we're going to use in the code below. This is a sample chat to try out the apply chat template function. In cell number 1, we are checking out the special tokens for a model. So here, if I run this cell, you will see that we are trying out the Google bird base uncased, and here are the special tokens for this tokenizer. Now, in order to change the model, you have to change the index here, which corresponds to the array in the first cell. So here you will check out the special tokens in use by the tokenizer. Next cell, we will check out the chat template for a given model. Again, you can set the model index to pick the model that you are interested in testing. Let me just stick to index equal to 0 and run this cell. And here you will see that the model is Llama 3.3 70B instruct, and it encoded the sample chat with the special tokens. In the third cell, I'm preparing the training data set for chat. This is the sample data that I'm using for creating the data set. And then when you run it, the messages in the conversation will get encoded with the special tokens. And fourth cell shows you how to set up a custom template. So go ahead, try out this exercise on your own. Happy learning, and I'll see you in the next lesson. In this quiz, you will be testing your knowledge of dataset formatting for fine-tuning. As always, if you need more time to answer the question, pause the video. Here comes the first question. Stanford alpaca is a blank. You have 10 seconds to answer the question. The correct answer is it's an instruct model. Next question. Datasets in alpaca format have following 3 fields for each instruction sample. The correct answer is instruction, input, and output. Recall that input is optional. Next question. Alpaca dataset, which has 52,000 instruction samples, was created synthetically using an LLM. True or false? The correct answer is true. Next question. You're fine-tuning Llama 3V instruct model. How would you format your domain instruction data? The correct answer is that you will need to use the instruction format that was used for fine-tuning the Llama 3V instruct model. Next question. All model tokenizers have a chat template defined in the configuration. True or false? The correct answer is false. Only the models that have been trained or fine-tuned for chat have the predefined chat template. Next question. You're preparing a domain data set for a chatbot. You will use Gamma 2V base model. Which formats can you use? You may use ChatML or you may define a custom format for your chat data. And the reason you can do the custom format is because it's a base model and it doesn't have a chat template defined in the tokenizer. Next question. Models use special tokens to flatten the conversation data. True or false? Correct answer is true. Next question. You are inferencing Llama 3V instruct model. The response quality is poor and response formatting is off too. What is the most likely reason for the observed behavior? The correct answer is query data is not formatted as per the model requirements. Next question. Data sets in ChatML format have following two fields for each message in the conversation. The correct answer is role and content. Next question. You're using a base model for fine-tuning a chat model. You can use a custom chat template. True or false? The correct answer is true. And this was the last question in the quiz. Happy learning, and I'll see you in the next video. In this lesson, you will learn about fine-tuning and hyperparameters. I'll start this lesson with the discussion on the fine-tuning process, followed by introduction to hyperparameters, and then I'll introduce you to the machine learning training experimentation, also known as hyperparameter tuning. At a high level, LLM fine-tuning leverages the same training techniques as the classical machine learning model. Domain adaptation fine-tuning uses a process like unsupervised training. Objective is for the model to learn the patterns in the data. The dataset used for such training is not labeled. Instruction fine-tuning uses a process like supervised training. This, as you have already seen, requires labeled datasets. Next, I'll walk you through the supervised model training process. We start by initializing the model with random values for the parameters, that is the weights and the biases. Next, we feed a labeled dataset into the training loop, which is a piece of code often written in Python. This training loop is responsible for training the model. The term loop indicates that the process repeats over multiple iterations. For each iteration in the training loop, there are two main steps: forward propagation and backward propagation. In the forward propagation, the model makes predictions in its current state without seeing the actual labels. Here, it generates the predicted values based solely on its current weights and biases. In this illustration, we see the actual values alongside the model's predicted values for each example in the dataset. Now let's look at the second part of the training known as backward propagation. In this step, we evaluate the model's predictions by comparing them to actual labels using a loss function. The loss function takes both the actual and the predicted values for each example and produces a single number that represents the model's overall error or loss for that iteration. Here is how it works. The loss function first calculates the difference between the predicted and the actual value. It then applies a mathematical operation to combine these differences into a single scalar value representing the loss. A common loss calculation method is mean squared error. With mean squared error, the difference between the predicted and actual value is squared, and the average of these squared value gives the final loss. The output from the loss function is then passed into the optimizer function. The optimizer's goal is to adjust the model's weights and biases to reduce the loss. To achieve this, optimizer uses a mathematical technique called gradient descent. At a high level, gradient descent examines the current weights and biases, determines whether each parameter should be increased or decreased, and then accordingly adjusts the parameters in the model. The training loop repeats this process over the dataset multiple times as specified by the user. There are multiple settings exposed by the training loop to influence the training loop's behavior. I'll talk about these settings in a few minutes, but let me first discuss model evaluation. To evaluate the prediction quality of the model, you need to run some tests on the trained or the fine-tuned model. These tests in the context of machine learning are known as model evaluations. Recall that in the fine-tuning exercises, you provided two data sets to the training process. A training data set that was used for training and a validation data set that was used for evaluating the fine-tuned model's performance. The evaluation process is similar to the forward propagation in model training. The validation dataset, which is an unseen dataset, is used for making predictions with the fine-tuned model. The predicted values and the actual values are then used by the loss function to calculate the loss. This loss value calculated in model evaluation phase is referred to as the validation loss. In addition, the predicted and the actual values are used for calculating various model quality metrics such as accuracy. Model tuners are able to gauge the quality of the training or fine-tuning based on the validation loss and the various model evaluation metrics. If they are not satisfied with the results, they tweak the settings on the training process and then rerun the training. In the context of fine-tuning, the configurations or settings for the training process are referred to as the hyperparameters. Hyperparameters are settings that the user specifies before the training process begins. The hyperparameter values guides how the training proceeds. These settings influence the way the model parameters are updated and refined. The hyperparameter settings have a direct impact on the quality of the model's predictions. Unfortunately, there is no simple way to determine the best values for hyperparameters. Finding the optimal value requires experimentation. Let me explain what I mean by experimentation in the context of machine learning. In fine-tuning experimentation, also known as hyperparameter tuning, We iteratively train a model with different sets of hyperparameter values. The objective is to identify the set of hyperparameters that produces the trained model with the best performance. Each fine-tuning run is called an experiment. For the first experiment, you will start by selecting an initial set of hyperparameter values guided by your past experience, intuition, or recommendation from the model provider. Then you will train the model using these values. After the training, you will evaluate the model's performance. The result of each experiment include key metrics such as training loss, validation loss, and other relevant performance measures, and these results guide you in adjusting the hyperparameter values for the next experiment. You will repeat this process experimenting with various hyperparameter configurations, and finally you will select the set of hyperparameters and the trained model artifacts that yields the best performance. That is, you would deploy the selected trained model for your applications to use in production. In this lesson, you learned about fine-tuning process and hyperparameters. For instruction fine-tuning, a labeled training data set is used. Fine-tuning is an iterative process. It begins with a model with random weights. Predictions are made using the current state of the model. A loss function is then used for calculating the magnitude of error between the actual and the predicted values. Then comes the optimizer function that uses gradient descent technique to estimate the adjustments needed for the model parameter. At the end of the iteration, the model weights gets updated. This iterative process continues for the specified number of iterations. The number of iterations are controlled by the hyperparameters. Hyperparameters are settings that control the behavior of the fine-tuning process. The optimal values for the various settings or hyperparameters for the training process is determined by way of experimentation. In the next lesson, you will learn about the commonly used hyperparameters in machine learning and large language model fine-tuning. Happy learning, and I'll see you in the next video. I'll start this lesson with an introduction to two key concepts in fine-tuning: overfitting and underfitting. You will then learn about commonly used hyperparameters for fine-tuning large language models. Finally, I'll cover the early stopping mechanism and its importance in the fine-tuning process. Overfitting, in the context of model training and fine-tuning, refers to the scenario in which the model becomes too specialized to the training data. The model essentially memorizes the training data instead of learning the underlying patterns. As a result, the model performs poorly on the unseen data. The symptoms of overfitting are that the trained model performs extremely well on the training data sets or the training examples, and at the same time, the trained model performs poorly on the validation data set. Now, keep in mind that the model during training has not been exposed to the validation data set. Underfitting occurs when a model is too simple to capture the underlying patterns in the training data. Common causes of underfitting are insufficient data or the training process is prematurely stopped. Symptom for underfitting is that the trained model performs poorly on both the training and the validation dataset. The first hyperparameter that I'll discuss is the epoch. Recall that fine-tuning process is iterative. Training is commonly carried out with the same training dataset multiple times. The hyperparameter epoch is used for setting the number of iterations. So if you set the epoch equal to 3, the training process will run the training loop 3 times over the entire dataset. The model parameters will be updated 3 times during the entire training, once in each iteration. Multiple epochs are often used to gradually improve the model's performance, with each epoch allowing the model to refine its understanding based on feedback from previous iterations or passes. A training iteration is sometimes referred to as an epoch or step. The next hyperparameter is the batch size. The training samples that are processed in an iteration needs to be loaded into the memory. For example, if there are 100,000 samples in the dataset and each sample is 100 KB, then 10 GB of VRAM is needed to run the training on a GPU. In effect, a large dataset would require higher amounts of memory. The batch size parameter is used for controlling the number of samples. In effect, it is used for controlling the amount of memory needed in an iteration. The idea is to divide the dataset into multiple subsets. So here I'm showing a scenario in which the batch size is set to 4. Only one subset is processed during an iteration. So in this example, subset 1 gets processed in iteration 1, subset 2 gets processed in iteration 2, and so on. With this setup, the model will get updated 4 times in an epoch. Now let's take a look at another example that will clarify how the batch size is related to epoch. Let's say your training dataset has 32,000 examples and you set the number of epochs equal to 3. If we set the batch size equal to 32, the dataset will be divided into 1000 batches or subsets. So the model will make 1000 updates per epoch, and with 3 epochs, this will result in a total of 3000 iterations or steps. Now, let's talk about how to decide on the batch size. Typically, batch sizes are set as numbers that are powers of 2. Batch size of 16 and 32 are considered small. These are often used for smaller datasets and when computational resources are limited. A batch size of 64 and 128 are considered medium. This is a common choice for many tasks, and a batch size of 256 and 512 are considered large. These are used for larger datasets when the computational resources are abundant. There are multiple factors that are used for deciding on the batch size. The first one is the size of the dataset itself. The training data must fit within the memory limits of the available hardware. Next one is the available hardware. If you're using a smaller GPU that is constrained on memory, then you would need to consider smaller batch size. GPUs with larger VRAMs are costlier. So if you have a budget constraint, then you may use smaller batch on smaller GPUs to save on the cost of fine-tuning. Next consideration is the task and the model in use. Some models and tasks perform better with specific batch sizes. Typically, model creators provide a suggestion on batch sizes for a task. In general, keep in mind that smaller batch sizes leads to use of lesser memory, they lead to better generalization, but at the same time, smaller batch sizes also lead to longer training times. The max steps parameter sets a limit on the total number of training steps. The idea is that it is observed that too many iterations have the potential of leading to overfitting of models. Overfitting is a scenario in which the model memorizes the training data and it does not perform well on unseen data. By limiting the number of training steps, we can reduce the risk of overfitting and save on computational resources. This is particularly useful when you are dealing with large data sets, limited hardware, or have training time constraints. Additionally, max steps is a valuable tool for experimentation. It allows you to quickly iterate on different model architectures and hyperparameters without committing to long training runs. Learning rate determines the magnitude of adjustment to the model parameter in each step. As you know, the optimizer determines the gradient or deviation for a model parameter. The amount of change made to the parameter is influenced by the learning rate. Here is a high-level formula for how the new parameter value is calculated. New parameter value is equal to old parameter value minus learning rate times the gradient calculated by the optimizer for the parameter. As you can see, the learning rate influences how quickly a model learns and adapts to the new information. A smaller learning rate requires more training steps and will take model longer to train. A larger learning rate leads to faster training, but at the same time, it may lead to poor quality of performance. As a rule of thumb, the learning rate should be adjusted according to the batch size. Smaller batch sizes may require smaller learning rates. So far, you have learned that same learning rate parameter value is applied to all of the layers in a model. Researchers have found that this is not the most optimal way of adjusting the model parameters in a step. Learning rate multiplier adds dynamicity to the parameter adjustment across the model layers. Learning rate multiplier parameter is used in conjunction with the learning rate parameter. The learning rate parameter, when used with learning rate multiplier, is referred to as the base learning rate. When the learning rate multiplier is set, higher layer adjustments are larger than the adjustments made to the lower layers of the model. Typically, model provider suggests a value range for the learning rate multiplier. Early stopping hyperparameters are a set of parameters that, as the name suggests, control the early termination or stopping of the training loop. The obvious question you may ask is, why would you want to do that? Why would you want to stop the training loop? Let me answer that question with an illustration. It is common to plot the training and the validation loss on a graph in which the loss is plotted on the y-axis and the epoch or training step number is plotted on the x-axis. After each iteration, the training loss and the validation loss are plotted on the graph. In this illustration, the blue line represents the training loss and the orange line is for the validation loss. In this illustration, we can clearly see that at this point in training, the validation loss and training loss or almost the same, and after that, the validation loss is increasing. Running additional steps after this point is not yielding any value but taking up time and resources. In addition, we see that the validation loss is increasing rapidly, and this is an indication of overfitting. Early stopping parameters help in saving time and resources, and they also prevent the model from overfitting. One important thing to keep in mind in regard to the early stopping hyperparameters is that these parameters can only be used if a validation dataset is provided. This is because the stopping mechanism relies on the validation loss to determine whether the training loop should be halted. Now that you understand the idea behind early stopping, let's look at the commonly used early stopping hyperparameters. The early stopping threshold is a hyperparameter that sets a limit on how much the validation loss can degrade before the training is halted. Let me explain this with an example. Let's say the early stopping threshold is set equal to 0.01. On the nth epoch, let's say the validation loss is 0.003. Since this validation loss is less than the threshold of 0.01, the training loop will continue with the next step. Let's assume that in the next step, the validation loss is 0.009. And since this is less than the threshold, training will continue with the next iteration. In the next iteration, let's say the validation loss is 0.015. Now, this is the point where the training loop will be halted as the threshold is breached. That is, the validation loss is greater than the threshold. No further steps will be carried out in the training loop and the training will end. The early stopping patience parameter determines how many consecutive epochs of non-improvement in the validation loss the training process will tolerate before halting. To explain patience, I'll use this illustration which highlights pronounced variations in the validation loss. Let's say the patience is set to 4 and the threshold is set to 0.01. Let's say on the nth iteration, the threshold is breached. Now, since early stopping patience is specified, the training will continue with the next iteration. The training loop on this breach will start a counter to track the consecutive breaches. And every time there is a threshold breach, the counter will be incremented. In the next two iterations, assume that there is a threshold breach. As a result, the counter value is now at 3. In the next iteration, let's assume that the validation loss fell below the threshold. This is when the counter will be reset and the training will continue. Now, as you can see, the training is not stopped immediately on the first breach of the threshold. This mechanism may lead to a trained model with better performance. In this two-part lesson, you learned about some of the commonly used hyperparameters for fine-tuning. The first set of parameters control the number of times the model weights are updated in the training loop. The learning rate parameters control the amount of change made to the model parameter values in each iteration. The early stopping parameters are used for controlling the early stopping or halting of the training loop. Keep in mind, these are some of the common hyperparameters used for fine-tuning. Depending on the model architecture, providers may expose additional hyperparameters that are specific to their models. As a best practice, always read the model card to learn about the hyperparameters supported by the model. Happy learning, and I'll see you in the next lesson. In this lesson, I'll introduce you to the checkpointing technique and the term checkpoint. Then I'll go over the benefits of checkpoints. Checkpointing is a technique in machine learning where the current state of the model's training is saved at specific intervals. This includes the model parameters, optimizer state, and other relevant information. These intermediate model assets or state is referred to as a checkpoint. These checkpoints are stored to a local or a remote storage device. Essentially, what that means is that with checkpointing enabled on model training, you will get multiple model assets that can be deployed for inferencing. The obvious choice will be a model that offers best performance. Let's go over the benefits of checkpointing. The first benefit is recovery from failures. If the training process is interrupted due to power outages, hardware failures, or other unforeseen circumstances, you can resume training from the last checkpoint, avoiding the need to start from scratch. Next one is experimentation and hyperparameter tuning. Checkpoints allow you to experiment with different hyperparameters and model architectures without losing significant progress. You can revert to previous checkpoints if a new experiment doesn't yield the desired results. Next one is early stopping. By monitoring the performance of the model on a validation set, you can stop training early if the model's performance starts to degrade, saving time and resources. The last one is model ensembling. Model ensembling refers to a technique in which multiple checkpoints can be combined to create a more robust and accurate model. In this lesson, you learned about checkpointing. Most machine learning frameworks offer checkpointing support. As a best practice, enable checkpointing when available, as it'll significantly improve the efficiency and reliability of your ML training and fine-tuning projects. In the next hands-on exercise, you will explore the hyperparameter and checkpointing features available in certain models. Happy learning, and I'll see you in the next video. In this exercise, you will delve into the fine-tuning hyperparameters supported by these models. Additionally, you will explore recommended values for these hyperparameters to optimize model performance. Instead of manually searching the model documentation, you can use an AI tool such as Google Notebook LM. The instructions provided in the course guide assumes that you are using Notebook LM. Let me give you a quick idea on what is Google Notebook LM. Google Notebook LM is an AI-powered note-taking and research assistant that helps you organize and understand your information more effectively. To use it, you need to sign in with your Google ID. On the Notebook LM, you need to create a new notebook. Once you have created the notebook, you add sources of information to the notebook. The information can be provided to the notebook by way of Google Docs, by providing the link to a website or link to a YouTube video, and you can even copy and paste your information as a source in your notebook. If you're new to Google Notebook LM, I suggest that you pause this video and explore it for a few minutes. It's a great tool that you can use for achieving high productivity with your knowledge tasks. Next, I'll walk you through the instructions. Instructions for this exercise are available in the course guide under the section Fine Tuning, exercise number 4, Explore Hyperparameters. I've provided the link to Google Notebook LM. The first model that we're going to explore is Gemini. The way it'll work is you will create a notebook and then you will add the link to Gemini documentation that I have provided as a source of information. You'll select the source within the notebook LM and then use these two prompts to explore the hyperparameters. You'll repeat the same exercise for OpenAI. Now, one thing that you will notice here is this warning. Basically, when I tried OpenAI documentation link as a source of information in the notebook LM, it failed. So what you need to do is copy and paste the content from the documentation for OpenAI as a source in the notebook LM and then use these two prompts. The third model that you're going to explore is the Cohere family of models. You'll repeat the same process, provide the documentation link as a source, run these two prompts to get the information about hyperparameters supported by the Cohere family of models. Last thing we'll do is you will find common themes for fine-tuning across the 3 family of models that we have explored in this exercise. Go ahead, pause the video and try out this exercise on your own. Next, I'll walk you through the steps for Gemini. I'm on the notebook lm.google page. Click on Try Notebook. I'm going to create a new notebook. Here, I need to provide the sources of information. The first source of information that we're going to provide is the link to the website with information on Gemini fine-tuning. The link is available in the course guide. Here is the information on fine-tuning the Google Gemini model. Just copy it and paste it as a link in the notebook. At this time, notebook is reading the information from the page. It generates a nice summary. And now we can ask some questions. To ask the question, I'm going to go back to the course guide and copy the first prompt, which is to list the adjustable hyperparameters for fine-tuning Google Gemini models. And here are the set of hyperparameters supported for Google Gemini models. As a next question, we're going to ask Notebook LM to provide recommendations for optimal hyperparameter settings for the Gemini family of models. We want the notebook to include specific values or ranges and explain their impact on model performance where applicable. Let me copy this, paste it in the notebook and wait for the response. And here is a summarized version of the documentation with recommendations on how to set up the hyperparameters for fine-tuning a Google Gemini model. So go ahead, try this out for OpenAI, Cohere, and then use the information to identify common themes in the fine-tuning recommendations. For your convenience, I've added the outcome of this exercise under the solution section. You can check out the various hyperparameters supported by Gemini, OpenAI, and Cohere model. One thing to notice here is that early stopping hyperparameters are supported only by Cohere, and another thing that you will notice is that OpenAI does not expose learning rate, but it exposes only learning rate multiplier. In addition, you will find a couple of model-specific hyperparameters. For example, eval percentage and epoch count are hyperparameters that are supported by Cohere only. To get more information on these hyperparameters, check out the documentation. Happy learning, and I'll see you in the next lesson. In this lesson, you learn about Hugging Face transformer classes used for fine-tuning the open source models available on Hugging Face. I'll cover the training class that is used for fine-tuning models, the training arguments class, and the data collator classes. The Hugging Face transformers trainer class is a powerful utility that implements the model fine-tuning loop. It makes it easier to train and evaluate models for a wide range of NLP tasks. It abstracts much of the complexity involved in setting up training pipelines, handling tasks like data loading, optimization, evaluation, and logging. The training class supports key functionalities such as automated checkpointing, early stopping, metrics computation, etc. It can also be easily extended to include custom loss functions, evaluation metrics, and data preprocessing. All of these features are available via configuration flexibility offered by the trainer class. An important point to keep in mind here is that the trainer class is used both for pre-training a model and for fine-tuning a model. The only difference is in the task for which the model is getting trained. The process for setting up the trainer remains the same. The trainer class takes in the base model, which provides the starting weights for fine-tuning. It requires you to provide the training data set, and optionally, you can also provide the evaluation data set. Trainer is configured by way of an instance of training arguments class. This class allows you to set up the hyperparameters for fine-tuning. You can configure the distributed or parallelized training, control the logging and reporting, and much more. Let's take a look at the documentation for the training arguments class. Let's take a quick look at some of the parameters that this class exposes. There are 116 parameters. I won't go through all of them. Here is the parameter that decides the output directory for the model checkpoints and predictions. You can configure the various hyperparameters. Just look for the parameters that you are interested in. Here is the learning rate. Here is the parameter for max steps. These are the warm-up parameters. And here are the logging parameters. There are quite a few logging parameters that are available to you for configuring the logging behavior of the trainer. Here is the save strategy, which basically controls the checkpointing behavior. Idea is that if you would like to persist the current state of the model, then you set it to either epoch, steps, or BESS. There are lots of other interesting parameters here. So my suggestion to you is pause the video and go through this documentation for a few minutes. Data collators are utility classes that are used for creating batches from data sets. Let's dive deeper into the use of data collators. Data collators simplifies the process of preparing data for model training. Their primary function is to create data batches for training and evaluation. In natural language processing tasks, input sequences can vary in length, and models typically require fixed length sequences to process them in batches. Data collators handle padding dynamically at the batch level. Now, this aspect will become clear once you will see data collator padding in action. Data collators also offer task-specific training data pre-processing. There are multiple data collator classes. You select the collator based on the task at hand. In this illustration, I'm showing the commonly used data collator classes. Data collator with padding allows you to carry out text and label padding lazily instead of padding the entire data set beforehand. In addition, the padding can be configured for maximum length string in the batch rather than the maximum length calculated from the entire data set. Data collator for sequence to sequence is a sequence to sequence NLP task specific data collator. The data set for sequence to sequence task has two text sequences that need to be padded. An example of sequence to sequence task is machine translation, let's say from English to French. So the first sentence will be English, the second sentence will be French. Now keep in mind the length of the two sentences or sequences may be different. The data collator for sequence to sequence is intelligent enough to calculate the required padding for the two sentences or sequences. Data collator for language modeling is another task-specific collator. In the mask language modeling task, as I discussed earlier, for training a model, you need to mask certain tokens and make the model predict the mask token in the training loop. The data collator for language modeling provides a simple way to configure the dataset for MLM or masked language modeling task. Now, don't worry if the idea of data collators is not clear. It will become clear once you will see the data collators in action in the next hands-on exercise. In this lesson, I covered the transformers trainer, training arguments, and the data collator classes. Transformer trainer class makes it easy to carry out fine-tuning. Transformer training arguments is used for configuring the trainer's behavior. Data collator classes are used for batching, padding, and for task-specific preprocessing. In the next two hands-on exercises, you will see all of these classes in action. Happy learning, and I'll see you in the next lesson. The objective for this hands-on exercise is to get hands-on experience with Hugging Face data collators. Details for the exercise are available under the Hugging Face section, exercise number 4, data collators. The first step I suggest here is to go through the documentation for the collators, then watch this video. It's a very nice video that explains how the various data collators work. And then you will open up this notebook either locally or on Google Colab, and then you will review the comments and the code in the notebook and try out the various data collators. Go ahead, pause this lesson and go through the documentation and the video. Next, I'll walk you through the code. In this notebook, you will find code samples for the commonly used data collators. The first one is the default data collator. The default data collator is a very simple data collator that requires you to provide the tokenized data, as it does not take tokenizer as the argument. Here in this first cell, you will see that I'm creating a synthetic data set, and then in the second cell, I'm tokenizing the data with padding. In effect, we are using the data collator only for batching and doing the padding outside of the collator. Here, as you can see, I set the max length equal to 20, which means that each of these sequences will have input IDs equal to 20, and that's what we are seeing here. This tokenized data is then passed to the collator, and it carries out the batching. As you can see here, I set the batch size equal to 2 by passing the collator just the two examples. And as a result, there are only two input ID arrays in the output from the collator. The next collator is the data collator with padding. This collator dynamically pads the input sequences. So let me just run this. I've statically tokenized the data to a length of 100, and this is just for demo purposes. And as you can see, each of the sequence in the data set is tokenized to an input IDs array with length equal to 100. Now if I do tokenization without padding, which is padding equal to false, each of the sequences have a different length input ID array. Models mostly expect the arrays to be of the same length. Now in the third part, we actually have the data collator with padding enabled, and here you will see that the length of each of the sequence is 10, and the reason the length is 10 is because this is the longest sequence and this is of length 10. So here, as you can see, the second sequence does not have any padding, whereas the first and the third sequence have padding, which is represented by the character with ID equal to 0. Now with the collator, since the ID array length is less than the statically set length, it will be much more memory efficient. At this time, I suggest that you go through the code in this notebook. Happy learning, and I'll see you in the next video. My objective in this hands-on lesson is to demystify the steps involved in the model pre-training. I'll start the lesson with an overview of the model architecture, dataset, and tokenizer that we will use for pre-training our model. Then I'll walk you through the code and run the code. Once our model will be trained, we'll test it out. Now, keep in mind that the trained model that we will create will have extremely poor performance. The objective of this exercise is to give you an idea on steps involved in pre-training, not to build a ready-to-use model. We will use the Roberta model architecture. The Roberta base model has been trained on 160 GB of data, which consists of the data sets I've listed here. It uses MLM for training. 15% of the tokens in the training data were masked. I suggest that you read through the Roberta base documentation before proceeding further. For pre-training, we will use the Hugging Face dataset acloudfan/wiki small. This was created from the Wikipedia English dataset. It has roughly 9,000 rows in training split and 1,000 rows in validation split. Before proceeding, I suggest that you browse through this dataset on Hugging Face Hub. And if you're interested in learning more about how this dataset was created, check out this notebook. For this exercise, our focus is on model pre-training. So we will not pre-train a tokenizer. We'll use the existing Roberta tokenizer fast in this exercise. Details for this exercise are available in the section Hugging Face. Keep in mind, my objective here is to show you how to use the Hugging Face trainer arguments and data collators for pre-training a model. The pre-trained model that will be created as a result of the training will have extremely poor performance as we are using a very small data set. Here is the structure of the notebook that we are going to use for pre-training. You will be opening up the notebook for pre-training in Google Colab. The last step in the notebook is to push the trained model to Hugging Face Hub. This step is optional. I've already done it for you. And so here you will see another link to Google Colab. This is for the test notebook. Next, I'll walk you through the pre-training notebook. I've already uploaded the notebook to Google Colab. The first thing we need to do is change the runtime. We will be using T4 GPU. Pre-training will be carried out in 8 steps. I'll go through each of these steps one by one. The first thing that we need to do is that we need to install the packages. You will see that I'm also including the accelerate package, which is needed by the trainer class. So let's go ahead and install the packages, import, and now we're ready to load the data set. I will be loading the aCloudFan Wiki small data set, and you already know how to load the data set. The data set is loaded. As a next step, we need to tokenize this data set. To do that, we will be using Roberta-based tokenizer, using the auto tokenizer to create the tokenizer instance. An instance of the Roberta tokenizer fast is created. Next, I'm creating a tokenize function that takes a set of rows and tokenize them. Run it. Now to apply this function to the rows in the data set, I will use the dataset.map function. Here I'll specify the function name. It is bashed, and then provide the column names. Now, the reason this is being done is to delete the original columns in the data set, as there will be 3 new columns added to the data set, and those are the columns that we're going to use. It'll become clear in a few seconds. Here is the variable column names, which has all the feature names or the column names from the data set. Run it, and here is our tokenized data set. As you can see here, we have the input IDs, attention mask, and special token mask, and the original columns from the data set are removed. Now that we are ready with the tokenized data set, we can go to the data preprocessing step. Here we will be defining a chunking function, a grouping function. We will decide on a block size. Then we will pass an argument to the function, which will be an array of tokenized data set rows. Each set will consist of n rows. Within the function, we will concatenate the value for each of the features, that is for input sequence, for special tokens, and for the attention mask. We'll just concatenate those. Then we will create groups with size equal to the block size that we are going to set. We will discard the last chunk if it is less than the block size. And then we will use the dataset.map function to apply chunking. So here is the function that does the grouping. You can go through this function on your own. It's pretty straightforward. Here is how the map function is used. To apply the grouping function, here you can see the batch size as 1000. And just one more thing I want to show you here is that the block size is 128, which means that once this function is applied, we will have data in the form of arrays, which will be of size 128 each. Let's go ahead and run it. And here is how the data set looks like after we have applied the grouping function to the rows. Next, we create the data collator. We are setting the MLM probability to 0.15 and passing the tokenizer. Run it, and we are ready with the collator. Next is the setting up of the training arguments. To do that, we will use the training arguments class. I'm setting the number of epochs equal to 5. Evaluation strategy equal to epoch means that the results from the training will be evaluated after every epoch, and we'll see the results printed out during the training. This is the learning rate, and here I'm saying use CPU equal to false because we don't want the trainer class to just use the CPU. If GPU is available, then we would prefer to use GPUs, and that's exactly the reason why we had selected the T4 GPU. Let me just click on this and you can see the system resources here. Let's go ahead and run it. Training argument is created. Next, we will create the model with the configuration for Roberta-base, and after the execution of this step, we will have the model ready for trainer. Next, we'll set up the trainer. We pass the model, we pass the training arguments, then we pass in the train data set, which is the train split, and the evaluation data set, which is available in the validation split. We pass it the data collator. and then we run the train. The duration that it takes for the training to complete depends on multiple factors, such as the size of the data set, such as the learning rate, number of epochs, and the allocated resources. On GPUs, it'll be faster, and on CPUs, it'll be extremely slow. Keep in mind that we are using a very small data set and we are running the training on GPUs, so I expect it to be very fast. We've already completed the first epoch in roughly 2 minutes. So now we have completed 3 epochs, and with each epoch, we can see that the training and validation loss is going down, which is good, which is what we expect to see during training. Training has now completed, and as a next step, which is optional, you can push the model to the hub. I'll skip this step as I've already pushed the model to the hub. I'll use the notebook TestWiki Small Roberta for testing out this pre-trained model. I'll carry out this test in 2 stages. First, we will use Roberta base model to predict a masked word. The sentence is, Mary has a little mask, and you know the answer. So let's go ahead and run it. The model has predicted lamb 14%, which is what we expected, pet 12%, etc. So these are the predictions from the base model. Now let's see what our pre-trained model is going to predict. Same sentence, I'm using the model that is available on the hub, and here are the responses. Period, punctuation mark 5%, the 4%, comma 3%. As you can see, the model is not really great in predicting the masked tokens, and that is because we have hardly used any data for training the model. At this point, I suggest that you go through the pre-training code on your own. Keep in mind, pre-training is not an easy task. My objective here was just to demonstrate to you how pre-training is carried out. Happy learning, and I'll see you in the next class. In this lesson, you will use the Hugging Face Transformers Trainer class to instruction fine-tune a model for the sentiment analysis task. As part of this exercise, you will adjust the hyperparameters to learn their effects on training loop and the performance of the model. Full fine-tuning refers to a training process in which all model parameters of the base model are a candidate for change, meaning the fine-tuning loop will potentially update a majority of the model weights and biases. This mechanism is rarely used as it suffers from various challenges. My intent here is to show you the full fine-tuning process for comparison purposes and to keep things simple. In later lessons, you will learn about parameter efficient fine-tuning technique that addresses some of the challenges associated with full fine-tuning. We will be using the Google BERT-based uncased model, which is an encoder-only model with 110 million trainable parameters. This model is trained on 2 language modeling tasks, the masked language modeling and next sentence prediction. As a result, it will perform poorly on NLP tasks for sentiment analysis. Our objective is to instruction fine-tune this model for sentiment analysis. Next, I'll provide you an overview of the notebook that we will be using in this exercise. The notebook begins with the setup of the device on which the training will be run. Then we will create a utility function for evaluating the model for the sentiment analysis task. We'll load the Stanford NLP IMDb data that we will use as the training data set. There are 25,000 training examples in the IMDb data set. Now, 25,000 is a big number unless you have a bigger GPU. So we will optionally reduce the size of the data set. Next, We will tokenize the training and the test data sets. We will be statically padding the text in the sentiment analysis examples. Then we'll set up the training arguments and the trainer. In the training arguments, you will have the opportunity to adjust the hyperparameters and other configuration parameters for the training loop. You will run the training and then evaluate the fine-tuned model for the sentiment analysis task. You will optionally save the model assets locally. And then you can also optionally push the trained model to Hugging Face Hub. In this setup, we are not using the data collator. Batching is carried out by the trainer itself. Details for the exercise are available under the section Hugging Face in the course guide. Let me walk you through the steps that you need to carry out. You will be opening up the notebook that I have provided in Google Colab. First step will be to review the IMDb dataset that we are using for fine-tuning the model. Next, you will review the documentation for AutoModel for sequence classification. You will review and run the code in the notebook cell by cell. After that, you will adjust the hyperparameters for experimentation. After you reset the hyperparameters, you will be retraining the model. And for that, you will need to restart the kernel or the session, and then you need to run all the cells for fine-tuning. Next, I'll walk you through the notebook. I've opened the notebook on Google Colab. The first thing we need to do is change the runtime to T4 GPU and save it. Keep in mind that there is a fixed quota you have, or the duration you have, for using the T4 GPUs on Google Colab. Once you run out of the quota, you won't be able to use T4 GPUs for a period of time. So let's go ahead and connect. Now that we have the GPU, we can look at the resources in use. As you can see here, we have 15 GB of RAM available to us and 112 gigabytes of disk space, which is good for fine-tuning this small model. First thing we'll do is install the required packages. Once the packages are installed, we can optionally try out the fine-tuned model that I've already uploaded to Hugging Face Hub. Now, this is an optional step. Here we are setting up the device that we will be using for training. The idea is that if GPU is available, the device is set to CUDA:0. Here we are defining the utility function for evaluating the model for sentiment analysis task. You will see that there are 4 text strings or sequences provided as a data set. The model is used for carrying out the prediction for these sentences, and the results are simply printed. So here in this cell, we are running this evaluation on the base model. And obviously we don't expect good results, as the BERT-based uncased model is not trained for sentiment analysis. So here, as you can see, we have received a predicted label of 0 for all of the text strings that we have provided. By the way, label equal to 0 is negative and label equal to 1 is positive. It is all fun, should have been positive, but we are getting a 0 here. So as expected, since the model is not trained for sentiment analysis, it is giving a very poor performance. Next, we will load the IMDb data set from Hugging Face. There are 25,000 samples in the train split of the data set. This would require a large amount of GPU VRAM. And for this simple task, we really don't need 25,000 examples. So in the next cell, we are going to reduce the size of the data set to 5,000. Now you can adjust this number as per your needs. I'm setting it to 5,000 because this has given me good results. So you shuffle the data set and then you select the number of desired records. After that, we are splitting the data set such that 10% of the examples are made part of the test split and 90% examples are in the train split. Then we tokenize the data set. We're defining a tokenize function here and then using the map on the data set to tokenize. Now comes the fun part where we are setting the training arguments and the trainer. As you can see here, these are the hyperparameters. This is where we are setting up the trainer with minimal number of arguments. Check the documentation to find out other arguments that are available on the trainer class. Let's run this. And now we are ready for training. Training will take some time. While the training is running, you can check out the resource usage on the resources panel for the GPU. Keep in mind that fine-tuning will take some time to complete. So I'm going to pause the video and resume once the training is completed. Full fine-tuning took roughly 16 minutes. Now that our model is fine-tuned, we can run a simple evaluation on the fine-tuned model. Let me run it. And this time, as you can see, we have the right labels. This is a positive sentiment. The label is 1. I didn't like this product is a negative sentiment. As a result, the label is 0. The book was okay, not great, but terrible, but not terrible either. For some reason, it is marked as negative. It is all fun, which is positive with the label equal to 1. The last two cells here allow you to save the model locally. And this cell here is for uploading the fine-tuned model to the hub. So if you decide to use a different data set, a different model, I will encourage you to upload the model to Hugging Face Hub and share it in the comments so that other students can try out your model. Don't forget to provide details of which data set you use for fine-tuning or which model you use for fine-tuning. Happy learning, and I'll see you in the next lesson. In this quiz, you will check your understanding of fine-tuning and hyperparameters. For each question, you'll get 10 seconds, and if you need more time, please pause the video. Here comes the first question. Hyperparameter value for max steps overrides the value for epoch. True or false? The correct answer is true. Next question. Hyperparameter batch size helps with running fine-tuning on smaller GPUs that have lower VRAM. True or false? The correct answer is true. Next question. You're given a data set with 3200 training samples. The hyperparameter epoch is set to a value of 3 and the batch size is set to a value of 32. How many times will the model weights be updated in the training loop? The correct answer is 300. The way you will calculate it is, you will divide the number of examples by the batch size. So that will be 3200 divided by 32, which comes to 100 times 3 times. So that's how the answer is 300. Next question. Same question, but this time the hyperparameter max steps is set equal to 10. How many times will the model weights be updated? The correct answer is 10. The reason is that trainer will forcefully stop the training after the max steps which is 10. Next question. A smaller value for learning rate may lead to longer training time as the model may take longer to converge. True or false? The correct answer is true. Next question. Learning rate multiplier introduces blank to the learning rate. The correct answer is dynamicity. Next question. A smaller value for hyperparameter batch size requires the learning rate to be smaller or larger? The correct answer is smaller. Next question. Hugging Face data collator classes are used for select all that applies. Data collators are used for batching, padding, and task data preprocessing. Next question. Hugging Face trainer class requires the hyperparameters to be passed in blank. You need to pass the hyperparameters in an instance of the training arguments class. Last question. Hugging Face trainer class is used for the correct answer is it is used for model pre-training, domain adaptation, as well as for instruction fine-tuning. Hope you enjoyed this quiz. Happy learning, and I'll see you in the next video. Training of generative AI models require powerful hardware like GPUs. I'll begin this lesson with an overview of floating point number precision, followed by an introduction to GPUs and CUDA. Let's start with a discussion on floating point precision. In numerical terms, precision refers to the exactness or level of detail with which a number is expressed, particularly when dealing with floating point numbers or decimal numbers. For example, 3.14159 has greater precision than 3.14 because it includes more digits after the decimal point, providing a more accurate representation of the value. A double precision floating point number, also referred to as FP64, uses 64 bits or 8 bytes, and it allocates 52 bits for the mantissa or the fractional part, which controls the precision. For instance, the number 602,000 in scientific notation is represented by 6.02 times 10 to the power of 5. Here, 6.02 is stored in the 52-bit mantissa, while the exponent 5 is handled by the 11 exponent bits. In contrast, a single precision floating point number or FP32 typically reserves 23 bits for the mantissa, which means lower precision compared to FP64. What do you think a half precision floating point number will look like? The half precision or FP16 uses 16 bits or 2 bytes. It allocates 10 bits for the mantissa, which is the fractional part, and 5 bits for the exponent. By the way, in each of these representations, 1 bit is reserved for the sign. You might wonder why we don't always use the highest precision numbers for the most accurate results. The reason is that in the context of large language models, numerical precision directly impacts the cost of training and inference. While the higher precision can lead to more accurate results, it also demands significantly more storage, memory, and computational power, which translates to higher cost. Most large language models are typically trained using floating point 32 or FP32 precision because it offers a good balance between numerical precision and computational efficiency. Let's dive a bit deeper. Model training involves an enormous number of floating point computations. There are several key factors that influence the number of computations needed for training. First one is the model architecture. For instance, a model with 7 billion parameters requires more than twice the floating point computations compared to a model with 2 billion parameters. The size of the training data directly affects the number of computations. Hyperparameters. Parameters like epoch significantly impact the computational load. For example, setting the epoch to 1 means that the model is exposed to the training data only once, whereas setting epoch to 7 would mean that the data is passed through the model 7 times for training. The choice of hardware is critical. GPUs, or graphic processing unit, designed for parallel processing are commonly used for model training and inferencing due to their ability to handle the intensive calculations involved in training. Balancing these factors, especially the hardware, is key to managing the trade-off between training time and the cost. Now, even with hundreds of GPUs, training a large language model like Llama 7B is estimated to have taken weeks to months. Some estimates suggest that it required 10 to the power of 25 floating point operations to complete. Next, I'll zoom in on GPUs. A graphics processing unit, or GPU, is a specialized processor initially designed to accelerate the rendering of images, animations, and videos for display. GPUs were originally designed for and used in gaming systems for rendering graphics that required a large number of computations. Unlike a CPU, which is optimized for general purpose tasks, a GPU excels at parallel processing, allowing it to handle many calculations simultaneously. This parallelism makes the GPU highly efficient for tasks that involve large-scale data processing, such as model training and inferencing in machine learning and AI, where high computational throughput is essential. Use of GPUs lead to reducing of training time. It accelerates the processing of large data sets and complex models. It reduces the inference latency, which means it enables faster predictions by handling parallel computations efficiently. But at the same time, it leads to higher hardware and operational costs compared to CPUs. A GPU's power is measured in terms of number of floating point operations that it can carry out per second. Here is a chart that compares the floating point 64 benchmark results for comparison purposes. M2 Ultra and Intel Core 7 are CPUs made by Apple and Intel respectively. All others are GPUs made by NVIDIA. The A100 GPU provides the most efficient compute at 5 trillion floating point operations per second for double precision numbers, or FP64. Now, it is important to note that GPUs are optimized for certain precisions. So if we look at FP32 benchmark results, we find that Apple M2 performs better than Intel Core 7, and NVIDIA A100 has dropped to the 4th position. NVIDIA GeoForce RTX 4090 is at the top with the 45 trillion floating point operations per second for the single precision benchmark or FP32 benchmark. For the FP16 benchmarking, the floating point operation measures for the GPUs are just doubling compared to FP32. Next, I'll discuss what is CUDA. CUDA stands for Compute Unified Device Architecture. It is a parallel computing platform and an API model that allows developers to write code that can take advantage of NVIDIA GPUs with ease. From the developer's perspective, think of it as an SDK, a library, or a package that you can use in your own code. CUDA provides a high-level API that abstracts away the complexities of GPU programming, making it easier for developers to write efficient parallel code. CUDA code can be compiled and run on a variety of NVIDIA GPUs, ensuring portability and compatibility across different hardware platforms. In other words, switching to a different GPU would not require you to change the code. CUDA optimizes the use of NVIDIA GPUs for applications. As a result, use of it generally leads to better performance. And last but not the least, CUDA integrates seamlessly with popular languages like C, C++, and Python, making it accessible to a wide range of developers. While NVIDIA is the leading GPU vendor, there are other GPU manufacturers that offer their own set of SDKs and libraries for programming their GPUs. These include AMD and Intel, each with their own proprietary platforms and APIs for parallel computing. Now, for the sake of completeness, I'll introduce you to another specialized hardware for compute efficiency. A tensor processing unit or TPU is a specialized hardware designed specifically for machine learning tasks, particularly those involving large-scale matrix operations. TPUs are developed by Google and they are optimized for the types of calculations commonly found in deep learning models. Time to go over the key points from this lesson. Most LLMs use 32-bit floating point numbers for weights and activations. Activation refers to the output generated by the neuron. GPUs makes training and inferencing faster. CUDA platform makes it easy to take advantage of NVIDIA GPUs. Happy learning, and I'll see you in the next video. In the last lesson, you learned about the need for GPUs for training large language models. In this lesson, we'll shift our focus to compute needs for inferencing. I'll begin this lesson with a discussion on factors that control the inference latency. Then I'll discuss how models use the GPU resources for inferencing, followed by an introduction to model compression techniques. Model inferencing involves a significant number of floating point operations, which directly impacts the inference latency or throughput. The number of floating point operations and thus the inference latency depends on several factors. First one is the input and output sequence length. For example, in a chatbot, input sequences are typically short, leading to faster responses due to fewer computations. In contrast, use cases like document analysis involves longer input sequences, resulting in higher latency as more computations are required. Similarly, the length of output also affects the latency. Generating a larger amount of text takes longer compared to generating a smaller amount as it requires more computations. Model size also plays an important role. A model that will fit in the memory of a server will provide better performance. As with training, inference performance is heavily dependent on the hardware used for hosting the model. GPUs, for instance, can significantly speed up inference due to their parallel compute capability. To give you a sense of scale, a 7 billion parameter model like Llama 7B requires billions of floating point operations for tasks like question answering. Another hardware factor is memory. Let's dive a little bit deeper into the dependency on memory. The parameter weights for the model need to be loaded in the memory for faster processing. The amount of memory needed depends on the size of the model. Here is a set of LLMs and their approximate size on storage devices. It's not a surprise that larger models have larger storage footprint. For example, Llama 2B is approximately 4 GB in size, whereas Llama 13B is roughly 24 GB in size on a storage device. GPUs use their own dedicated memory instead of the RAM. This memory is known as video RAM or VRAM. It is a type of memory that is specifically designed for graphic processing units. It is a high bandwidth, high speed memory that stores data and instructions that the GPU needs to process. Unlike the system RAM or random access memory, which is used for general purpose computing, GPU memory is optimized for parallel processing and graphic intensive tasks. This means that it can handle large amounts of data and perform complex calculations very efficiently. Let's take a look at the GPU memory requirements for the models that I shared earlier. Llama 2B needs a minimum of 8 GB to provide decent performance, whereas Llama 13B requires a minimum of 32 GB for decent performance. By the way, these are just estimates. Now, if you have used local model hosting with, for example, Ollama and tried some of these models, you would have noticed a significant difference in the performance of the models. User experience for generative AI applications depends on the model latency. Slow responses for the model can turn off the application's users. In case of third-party hosted models, you don't have much of a choice, as the third party is responsible for managing the hosting infrastructure. In case of self-hosting, as a designer of the application, you will need to balance the acceptable model latency and the cost, which is predominantly going to be a spend on the GPUs. A reduction in inference latency would require you to use bigger GPUs, and that would translate into higher cost. On the flip side, if the cost is reduced in terms of the spend on the GPU, the latency will increase, and that may have a direct impact on the user's experience. Fortunately, there are techniques available to reduce the model size. Idea is that a smaller model requires less powerful compute and smaller memory, leading to lower cost. Model compression refers to a set of techniques that are used to reduce the size and computational complexity of the model. Model compression leads to faster inference times by reducing the model's computational requirements, which in turn lowers the energy consumption. This also allows the model to be hosted on smaller, less powerful GPUs without compromising the latency. However, these benefits come at a cost. Now, despite the advantages of model compression often results in reduced accuracy in the model's responses. Next, I'll introduce you to the various model compression techniques. The first technique is quantization. This involves reducing the precision of the model's weights and activations from 32-bit floating point numbers to lower precision numbers like FP16 or 8-bit integers. This can significantly reduce the model's size and computational cost. Next one is knowledge distillation technique. This involves training a smaller student model to mimic the behavior of a larger teacher model. This can transfer knowledge from the teacher model to the student model, allowing the student model to achieve similar performance with a smaller size. Next technique is known as pruning. This involves removing redundant or unimportant connections, that is, weights, from the model. This can reduce the model's size and computational complexity without sacrificing accuracy. And the last technique that I'll cover is the weight sharing technique, in which weights are shared between different layers or neurons in the model, reducing the number of parameters. I will dive into some of these techniques in later lessons. Let's go over the key points from this lesson. For inferencing, model weights are loaded to the memory for faster performance. GPUs are needed as model inferencing involves billions of computations. Models can be compressed so that they can be hosted on less powerful GPUs without any impact on model latency. You learn about the various compression techniques that lead to reduction in model size and computational complexity. A compressed model can be hosted on a smaller GPU, but it is important to keep in mind that model compression leads to some loss in model's accuracy. Happy learning, and I'll see you in the next video. In this quiz, you will test your understanding of use of GPUs for model training and inferencing. As always, pause the video if you need more time to answer a question. Here comes the first question. CUDA, or Compute Unified Device Architecture, refers to a proprietary platform for NVIDIA GPUs. True or false? The correct answer is true. Next question. Activation refers to the parameter weight, neuron's output, or the model's output. The correct answer is neuron's output. Next question. Inference latency depends on which factors? The correct answer is that all of these factors influence the inferencing latency. Next question. Following is the most used precision for the large language models. Select one. The correct answer is floating point 32. Next question. Model compression reduces model's memory footprint, model's use of compute resources, model's accuracy. The correct answer is it reduces model's memory footprint, model's use of compute resources, and to a certain degree it also reduces model's accuracy. Next question. Use of higher precision weights for LLM leads to higher cost of training and inferencing. It requires use of complex techniques. It requires use of GPU. It lowers the accuracy after certain precision. The two correct options here are it leads to higher cost of training and inferencing, and it requires use of GPUs. And this was the last question. Happy learning, and I'll see you in the next video. I'll start this lesson with a discussion on idea behind quantization technique, followed by a discussion on how the weights and activations for a model are quantized. Quantization is a model compression technique that reduces the precision of numerical values in a model's weights and activations. This helps with lowering of memory usage and computational requirements for the model during inference without significantly sacrificing the accuracy. Recall that most LLMs are trained with floating point 32-bit weights and activations. With most quantization schemes, the single precision numbers or FP32 in the model are replaced with half precision numbers, that is floating point 16 numbers. This type of quantization is straightforward since both data types follow the same representation scheme. Another common quantization scheme involves converting the single precision representations to integers, for example, an int 8 or a single byte integer. This conversion is not as easy as int 8 can only represent 256 values that need to represent an entire range of floating point 32 range of values. By the way, depending on the use case and accuracy requirements, models can be quantized to even smaller integers such as int 4. To give you an idea on resource savings, floating point 32 to int 8 conversion yields roughly 75% reduction in model size, and floating point 32 to int 4 quantization leads to roughly 87% reduction in the model size, which, as you know, will lead to reduced need for memory and reduced need for compute with a small impact on the accuracy of the model. Let me explain at a high level how the floating point 32 to int 8 quantization works. There are several techniques for quantization, but the one that I will focus on here is called scaling quantization. In FP32 or 32-bit floating point, we can represent a vast range of numbers. However, in int 8 or 8-bit integer, we can only represent 256 discrete values. To maintain symmetry around 0, scaling quantization typically ignores the value negative 128, giving us a balanced range for the int 8. This technique works by mapping the values from the FP32 range into the int 8 range. The process begins by identifying the minimum and the maximum values in the FP32 range. These corresponds to the smallest and the largest parameter weights respectively. In the quantization process, the minimum FP32 value is mapped to the negative 127 and the maximum is mapped to positive 127. A scaling factor is then applied, allowing all the values in the FP32 range to be accurately represented within the int 8 range. To recover the original value, we dequantify by applying the quantization process in reverse. While this restores the FP32 representation, some precision is lost in the process. Now, let me walk you through a simplified example to help illustrate this. Consider a scenario in which the min and the max values for a set of FP32 numbers is negative 500 and 500 respectively. The scale factor is calculated by dividing the max FP32 number by the max that int 8 can represent. So in this example, the scaling factor comes out to be roughly 4. To quantize, we can simply divide the FP32 number by scaling factor of 4. So in this example, floating point number 102.334 will be represented by an integer value equal to 26. To dequantize, we can simply multiply the int 8 representation by the scaling factor, which is 4 in this case. As you can see, the quantization and dequantization operation with this method led to a difference of roughly 1.7 between the original and the dequantized calculated value. This represents the loss in precision or accuracy. Keep in mind the technique that I described here is oversimplified. You will learn about other techniques that lead to minimal loss of accuracy. You have already learned that model weights can be quantized. This is relatively straightforward since the weights are static. It's simply a matter of finding the minimum and maximum values and then applying the scaling techniques. What's interesting is that activations can also be quantized. The challenge here is that activations aren't static like weights. They are generated dynamically at runtime. To quantize activations, a calibration dataset is used. This can either be the original datasets used for training the model, or it can be a smaller representative dataset. This dataset is fed to the model to generate the activations. These activations are then analyzed to determine their range, that is the minimum and the maximum values. In summary, both model weights and activations can be quantized. Let's recap the key points from this lesson. Quantization is a technique used to reduce a model's size by converting high precision weights and activations into lower precision formats. Quantizing weights is relatively simple since they are static. However, quantizing activations require a calibration dataset to generate the activations, which are then used to define the range for applying the quantization process. We covered high-level overview of scaling-based quantization, but there are many other techniques available through various libraries. In the next hands-on exercise, you will explore 2 different quantization techniques. Happy learning, and I'll see you in the next video. In this hands-on exercise, you will learn the basic mathematics behind quantization. You will walk through the provided code and run the code for comparing the performance with different precisions. The provided notebook covers 2 quantization techniques, affine and uniform. Instructions are available in the course guide under the section Quantization. Let's go over the steps. The first step is to review the affine technique. The link is already provided here in the guide. Here you will find a description of how the affine technique works. So go through it to understand at high level how the affine technique is implemented. I've also provided a step-by-step example that shows you how the technique is applied to the matrix of weights. Once you have an idea on the basics of affine technique, the next step is to open the notebook locally or in Google Colab. The location of the notebook is provided, or you can click on the Open in Colab button. In the third step, you will run through the code and compare the performance of affine technique for quantizing FP32 to int 8 and int 4. As a last step, you will walk through the code for the uniform quantization technique. This one is optional. So go ahead, pause the video and try out the exercise. Next, I'll walk you through the code. I'll open this notebook in Google Colab. In the first code cell, you will find a utility method called plot quantization. This is simply to plot the results of quantization and dequantization in a multi-bar chart. Here is the first method for quantization, affine quantize. This method takes an array of FP32. It also takes number of bits for the integer. So for example, for int 8, you will pass number of bits as 8. For int 4, you will pass it as 4. Here we are finding the min and the max values in the array, defining the scale factor, then defining the 0 point or the offset. And here is a expression to create the quantized value for the given array. After quantization, we are carrying out dequantization by applying the reverse formula and then returning back the quantized array as well as dequantized array. In this cell, we are creating some sample data. This is what I'm calling original, and then calling the affine quantize function with the original and number of bits. First I'm calling it for 32-bit, then 8-bit, then 4 bits. And then I'm plotting the bar charts for original and the dequantized arrays. So here is the bar chart that gets created as a result of execution of this cell. So here you can see that there is very little difference between the int 8 and the original, but there is a significant difference between the dequantized values for int 4. And you can see that based on the deviation between the blue and the green lines and the red line here. Optionally, you can go through the code for uniform quantization as well, which is defined as a function here. You will see very little difference between affine and uniform quantization. I hope you enjoyed this lesson. Happy learning, and I'll see you in the next video. In this lesson, you will learn when quantization techniques are applied. You will be introduced to the term post-training quantization, static and dynamic quantizations. I'll start this lesson with a quick one-question quiz. Try out your best to answer the question. When is the quantization technique applied? Here are your choices. During pre-training, after pre-training, or at the time of deployment, just before inferencing. Pause the video if you need more time. If you picked choice number 2 and choice number 3, then you are correct. Option number 1, during pre-training, is not correct. Pre-training leads to model that is trained with full precision weights and activations, and use of other precision will not count as quantization, as the model will be trained from the get-go with the desired lower precision numbers. Quantization applied after pre-training is known as post-training quantization. In this approach, the model is fully quantized before deployment for inference. This process, called static quantization, happens offline. Both the model weights and activations are quantized during this process. Since activations are quantized, a calibration dataset is required. This can either be the original training dataset for the model or a smaller representative sample. It's important to note that the quality of the calibration dataset will directly affect the accuracy of the quantized activations. Quantization can also occur dynamically during inference. This is referred to as the dynamic quantization. In this case, the quantization takes place when the model is loaded into memory for inferencing. A key difference here is that only the weights are quantized in the dynamic quantization. In some cases, a calibration dataset is needed for dynamic quantization as well, but it's used only for quantizing the weights, not the activations. Another technique known as quantization-aware training is applied during fine-tuning. In this section, you will learn about the post-training quantization, while the quantization-aware training will be covered later in the section on fine-tuning. Let's dive deeper into the post-training quantization with static approach. In this approach, the pre-trained model weights and a calibration dataset are provided to the quantization logic implemented in the form of a library. This stage of the process is often referred to as the calibration phase. At the end of the quantization process, a new version of the model is generated with its weights converted to lower precision. This quantized model can then be serialized, allowing it to be saved to a file system, or it can be added to a Git repository, or it can be hosted on model hubs like Hugging Face. The quantized model is now ready to be deployed without any further processing. The weights for the model gets loaded to the memory, and the applications can then leverage the quantized model for inferencing. Dynamic post-training quantization gets initiated at the time of model's deployment. A pre-trained model's weights are quantized in the initialization phase, followed by the deployment of the quantized model in memory. It's important to note that the quantization process is triggered during the model's deployment with the computations happening in the memory. Once deployed, the quantized model is ready for use by the model consumer for inferencing. There are several machine learning libraries and frameworks that make both static and dynamic quantization straightforward. Here are just few examples. In addition to these, many other open source libraries are available to further simplify the quantization process. In the upcoming hands-on exercises, you will explore dynamic quantization using PyTorch and static quantization with Hugging Face transformer-based AutoGPTQ library. Next, we'll explore some statically quantized models on Hugging Face portal. Let's look for Mistral, and I'll select Mistral 7B Instruct v0.3. Let's check the size of the model. This particular file, consolidated tensors, contains the weights for the model, and it is 14.5 GB. If we go back to the model card and look at the model tree, we will find other Hugging Face models that have been quantized using this model as the base model. So there are in all 90 models. Let's check those out. I'll just open up the first model here. As we can see here, this is a weights only quantization of Mistral 7B Instruct v0.3, and the quantization is for int4. The GPTQ library has been used, and the benchmarking of the quantized model indicates 99.75% accuracy recovery relative to the unquantized model. Let's look at the size of the model. Here, the model safe tensors file contains the weights, and as you can see, it is just 4.17 GB. So that's a significant saving in terms of storage and memory footprint. So I hope this gave you an idea on how to find quantized models on Hugging Face. My suggestion to you would be to explore the quantized versions of other popular models such as Llama and Qwen. In this lesson, you learned about post-training quantization. Static quantization is an offline process that creates a new version of the model that can be saved to a disk It can be published to a model hub. It can be deployed as an endpoint or used for in-memory inferencing. It involves quantizing of weights and activations, and some libraries also allow weights-only quantization. Dynamic quantization happens on the fly. The model is quantized at the time of deployment for inference. Dynamic quantization typically is supported for weights-only quantization. Now, there are multiple libraries available for static and dynamic quantization. You will try out both static and dynamic quantization in the next set of hands-on exercises. Happy learning, and I'll see you in the next video. In this hands-on exercise, our objective is to learn how LLMs are quantized dynamically for inferencing. We'll focus on comparing the accuracy and size of the original versus the quantized version of the model. Let me walk you through the course guide. Details of the exercise are available on the page exercise number 2 under the section titled Quantization. Before I proceed, I would like to mention that my intent here is not to teach PyTorch, but to demystify quantization and show its real benefits in terms of model compression without a significant loss of accuracy. So the way we'll carry out this exercise is the code is already provided. You will create a new notebook, and then you will start to copy the code from the guide into the new notebook. As you will copy, you will review the code and then run the code. There are 3 main parts in this notebook. The first part is to load the non-quantized model and invoke it. Then we will apply quantization from FP32 to int8. And here is the configuration for the quantization that you can adjust once you have a feel of how this is working. After the model is quantized, we will invoke the quantized model to compare the output from quantized model with the output from the original model. In part 3, we will compare the sizes of original model with the quantized model. So once you will run it, you will see what savings you're getting in terms of the storage of the model as well as the rough estimate around the saving of memory with the quantized model. If you have trouble running this notebook on your local machine, you can always use Colab. So go ahead, try out the exercise, and next I'll show you this notebook in action. I've opened the solution notebook in Google Colab. In part 1, we are loading the model and invoking it. The model that we are using is a 125 million parameter model. You can also try it out with another model that I have commented out here, but we'll go with the smaller model. Keep in mind that larger model may require use of GPUs for quantization. We're using the Hugging Face transformer library to invoke the model. So we are going to run this cell, and the input here is once upon a time, and the completion is I was a student at University of California. Output looks very logical and coherent. We will compare this output with the output for the same input from the quantized model. In part 2, we will apply the dynamic quantization using the PyTorch library. As you can see, it's a pretty straightforward task to use dynamic quantization with PyTorch. The 2 parameters that you provide to the quantized dynamic function call is the original model that we created in part 1, and then the targeted precision, which is int8. This will create a new version of the model. The next step is to basically invoke the model, and to invoke the model, we'll provide the same input that we provided to the original model. Let's go ahead and run this cell. The model was quantized, and take a look at the output. I was a student at the University of California, which is exactly the same as the original model. So it looks like we haven't lost any accuracy between the original and the quantized model. In part 3, we're going to compare the size of the quantized model with the size of the original model. To do that, I have a utility function here that writes out the model to the file system and then reads the file size. We do it for both the original and the quantized model and then print out the file sizes. So let's run it. And as you can see, the original model's size on the file system is 500 MB, whereas the quantized version has a size of 284 MB, which is a pretty significant saving without any indication of a loss in accuracy. Now, keep in mind that the results may vary with different models. So I highly recommend that you look for other models on Hugging Face to try out with dynamic quantization. I suggest that you pick up smaller models like the one I have here in the comments, like GPT-2. Happy learning, and I'll see you in the next lesson. In the last hands-on exercise, you saw dynamic quantization in action. In this exercise, you will work with static quantization. You will learn how to quantize a model using a calibration dataset, and you will also publish the quantized model to the Hugging Face space. Details of the exercise are available under the quantization section of the guide. Exercise number 3, quantize and publish. In step 1, you need to review the differences between static and dynamic quantization. Click on the link and you will be taken to a table that compares static and dynamic quantization. In step number 2, go through an overview of AutoGPTQ library. This is the library that we're going to use for static quantization. In step number 3, we'll open a notebook in Google Colab. The reason this notebook needs to be opened in Google Colab is because GPTQ is not supported on CPU. So in Colab, we'll be using the T4 GPU for running the code. Within the code, you will find the cell with code to publish the model to Hugging Face. So we'll do that, and then we will update the model card for your quantized version of the model on Hugging Face. Let me open up the notebook in Google Colab. The first thing we'll do is make sure that we have selected the right type. I have the T4 GPU selected. In the code, we are installing certain packages. Let me just go ahead and install these. And then next thing we are doing is setting up the calibration dataset. Let me run it. Next, we have the model ID set up, and then we are setting up the GPTQ config for quantization. Here, as you can see, the targeted model will have a precision of int 4, and we're also specifying the custom data set for calibration. And here is the line where we are carrying out the actual quantization by passing the quantization configuration. Once this cell is executed, we'll have the quantized model ready for testing. Keep in mind, the model needs to be downloaded and quantized, so it may take some time for the model to get ready. Once the quantized model is ready, we will test its performance. So let me just run this, and I'll pause the video for the quantization to complete. Quantization has completed, and here is the output from the invocation. As a next step, we're going to share this model on Hugging Face Hub. So this cell will ask me for the Hugging Face token, which I'm going to provide. Keep in mind that this token that you need to provide here must be writable. And now I will publish this 4-bit model, uncomment the appropriate line, and run it. It'll take a few seconds for the model to get published. Let's check the model, and this is the model under A Cloud Fan, and this is the name that we provided in the API. The model card here is empty, so you need to update it with appropriate information. Let me show you in my spaces where this model is appearing. Here is the 4-bit version of the model that I just created. So go ahead, follow the steps, and publish your model on Hugging Face Hub. Happy learning, and I'll see you in the next video. In this quiz, You will test your understanding of quantization and differences between static and dynamic quantization. As always, pause the video if you need more time for a question. Here comes the first question. Static quantization involves on-the-fly weight quantization just before model deployment for inferencing. True or false? The answer is false. Keep in mind that static quantization is an offline process. Next question. When is the quantization technique applied? The correct answer is after pre-training and at the time of deployment. Next question. Both weights and activations are quantized in static quantization. True or false? The correct answer is true. This is what differentiates static quantization from dynamic quantization. In dynamic quantization, only the weights are quantized. Next question. Calibration data set blanks the quantization. Your choices are optimizes, reduces, and magnifies. The correct answer is it optimizes. Next question. Calibration dataset is used for improving the accuracy of quantized models. It is used for weights, output, activations. Select all options that apply. The correct answer is weights and activations. Next question. Dynamic quantization involves on-the-fly weight quantization just before model deployment for inferencing. True or false? The correct answer is true. Next question. A dynamically quantized model from floating point 32 to int 8 will have activations in the following precision. Pick one. The correct answer is FP32. Recall that with dynamic quantization, only the weights are quantized. So in other words, the weights will be in the int 8 precision, but the activations will still be FP32. And this was the last question. Happy learning, and I'll see you in the next video.